did it. And this is medical doctor and statisticians that essentially follow on these steps of Sir Ronald Ross. Sir Ronald Ross was, in fact, attacking a much more harder problem than them. He was involved in the study of malaria. They were involved in the study of communicable diseases. Communicable diseases, that are the diseases that are transmitted from person to person. So this is Ronald Ross, and after he discovered the life cycle of malaria, the next question that came to him is, how can I, and this is the scaling up. You make some sort of discovery that is gonna help ameliorate the pain associated with malaria, the deaths, principally among your patients. Now you understand that. But the next thing is, how can I use this knowledge, acquire this information, how can I extrapolate this information in order to ameliorate the problem of malaria at the level of the city, region, country, the world? That's the way Sir Ronald Ross thought. And I think that that's the way that every single young person in this room should think about. So let me see if I, can you move it to the next one? I think, I went too far. Okay, so we go back one back. So here is a little movie. I mean, they are gonna work here, so this is terrific. You have all the right software here too. And this is why they discovered, but the general idea is he thought that he knew, like every good scientist, how he could stop the spread of malaria. And the way it does it is in science, what it is typical of all science, and we have a physicist here, is transition points. This is the key. Study the dynamics of how you move within a particular transition point. That's very complicated, but identifying transition points is critical, right? When you become from solid to liquid, et cetera, et cetera. So that's what transition points are about. So he said there is a transition point here too, like in most science. And if you bring the vector population, the mosquito population below some threshold, malaria can be controlled, or it would be it would be changed dramatically. And even though he had just won the Nobel Prize, they didn't believe him. So what does he do? He goes to mathematics and writes a set of equations to prove that his ideas have in fact merit. So here you have, this is the proportion of infected mosquitoes, and this is the proportions of humans that don't have an infection. And here is the proportion of infected humans with the malaria, and this is the proportion of non-infected mosquitoes. And then when he writes this equation, you immediately see factors like this, like M over M, which is the ratio of mosquitoes to humans. Of course, if there is a lot of mosquitoes, we're going to have a problem. And then here you see also the lifespan of humans, and here you see the lifespans of mosquitoes. So immediately you see ways of we can alter the dynamics. If we reduce this, there's going to be a change. If we reduce the lifespan of the mosquitoes, there's going to be a change. If we reduce the lifespan of the humans, we're not going to be happy, okay? So this is some of the things that they have. And then what he does is discover that there is a threshold based on this quantity. And for those of you, that threshold has to do the transition between exponential growth and non-exponential growth. But since we are epidemiologists, that's the transition between an expanding epidemic and a contracting epidemic. Mathematics, an expanding map and a contracted map. And essentially, if this is greater than 1, that means that every mosquito is going to pass via human an infection to more than 1 mosquito, or every human is going to pass the infection to more than 1 human on the average, right, via a mosquito. And then you can see this is the host vector ratio. This is these are dividing rates. This is the lifespan of the human, the lifespan of the vector. And immediately you see that if you alter this, you can go for something that is greater than 1 to something that it is less than 1. So let me summarize what Sir Ronald Ross did. He has this great discovery that helps us understand the dynamics of malaria from mosquito to human and vice versa. And then he wonders about the public good. Can malaria be controlled at the community or population or regional, national, or global levels? And this becomes a problem across scales. How do we use individual transmission knowledge to explain disease patterns at the population or regional level? And we know these are nonlinear problems, so the whole is not the sum of its parts. So this is the complication. That's an advantage and a complication. This mathematics helps. The identification of thresholds involving transmission and life history parameters addresses the usefulness of mathematics. And then this is really the mathematical part. The mathematical part, he writes this model all in an appendix. He writes, and he sets a precedent. The mathematics that are going to be useful, even if they are beautiful mathematics, they're not going to be at the forefront, because if you put it at the forefront, the people that are fighting diseases are not going to read the papers. So he put it in an appendix. And in the appendix, he says, by the way, among other things, he had beautiful ideas. These models can be used to study the transmission dynamics of sexually transmitted diseases. They're exactly mathematically, abstractly, they should have the same form. It took 60 years for mathematicians to read more science. And I have a consortium in Latin America that I've been developing over the last few years. And my big dream is to get people that are quantitatively trained, right, with scientists, because the agenda is set up by scientists, by public health officials. That's where the agenda comes from. And it can be set by mathematicians, unless we learn as much sciences, which is the case in some situations. And the general idea when you are studying problems of this nature is you have to have a dialogue. But that dialogue is not like I go to a meeting, talk to a couple of biologists, and they don't understand, and I come back and I can work with them. This is a life process. It's a total devotion to understanding, identifying problems, and then working day and night till you can make some progress on those problems. So I'm trying to do that, and the only way that we can do that is to bring in scientists to identify the central problems that we have, right? And in order to do that, there has to be an incentive. They don't want to come and hear mathematicians about proofs. They want to hear mathematicians about what they actually do to solve their problems. So this is an example. This is one of my former mentors. He's Kenneth Cook. He passed away at Pomona College. And this is Jim York. If you have heard the word chaos, this is the person that introduced the word chaos in mathematics when he wrote a paper by Lee called Period 3 Implies Chaos. These two individuals in the 70s wrote the first paper for the transmission dynamics of gonorrhea based on the work of Sir Ronald Ross. And they had lots of mathematics here. Then Herbert Heathcote and Jim York got involved in gonorrhea, and they decided, right, to address a problem that they saw in the control of gonorrhea. And the situation is, if you are a man and you have gonorrhea, you have symptoms, you have pain, so typically then you go and get antibiotics. If you are a woman, you don't. And the problem with that is by the time that you realize that you have gonorrhea, you have something often that is called pelvic inflammatory disease, and one of the consequences is that you cannot have children, or potential consequences of that. So the United States, what they used to do, every time a woman came for having a Pap test, they checked them to see if they have gonorrhea. And of course, overwhelmingly, they didn't, and they kept doing this. So they decided, let's do something different. So what they did is, let's be more realistic. Let's assume that there is two groups, what he calls the core group of bad boys and bad girls that don't behave very well, and others that behave semi-well. And the core group is the people that have many sexual partners. And what they did is, without data, because there was no data, they didn't know what the size of those groups. They estimated what happens if we focus on the core group, and they find out in a monograph, 100 pages monograph, that the most efficient way to do it was to focus on the core group, and that they could reduce, identify a case of gonorrhea, 20 cases of gonorrhea more than the ones that were being identified by the standard method. And instantly, the United States changed their policy. So you go to, I was in New York, Albany, the capital of New York, they have the map of all the sexually transmitted disease clinics. And when there is an outbreak of gonorrhea, they send the detectives there, they stop the usual suspects, and they say, what did you do this week? And then they treat them, and then they have reduced significantly the case of gonorrhea. And this was done with some models, very complicated models, but they could not even do mathematics with these models at that time, and they have changed the way policy was done. This is Ed Kaplan. And he is not a mathematician. He is in operations research. He's an engineer. He was the president of Inference recently. And what he did during the HIV epidemic, that's when I got involved in this. We got involved about 87. He got involved, and his goal was to reduce HIV transmission, right, due to the intravenous drug users. That was his general idea. And when he's looking at that intravenous drug users, he realizes that more or less this is the pattern of transmission. You have a group of people that are in a circle. Somebody has a needle, injects them. The needle gets infected, passes it to the next person, they inject it. They might or might not get infected, but they clean the needle. It goes to the next person, it doesn't have. So it's a complicated model, but essentially here you have two populations, the population of needles and the populations of intravenous drug users. You have vectors and hosts. The same model, a little bit more complicated. And he uses this model, and he buys a band, he proposes an exchange needle program, and it goes through a lot of controversy. And after a long series of studies, they prove that it's efficient and eventually gets implemented in New York. And it estimated that very quickly saved over 2,000 lives. This is, as a result of that, he's now a member of the 3 national academies. This was what's so important. Okay, this is a typical epidemic that you have here. This is a typical epidemic, and generally you look at data, you can, most epidemics look this way, and you can indeed fit models to data very well. This is what we were calling the expansive ratio, the basic reproductive number, 2.5. It says that each case of an infected person generates 2.5 cases. This is assuming that most people are not infected, and this is a smaller value, and this is more or less the kinds of curves that you get. And so here is an example of an epidemic in London, where you have in a school, and this is the outbreak. And you can use the very simple model. I didn't write it, but this is the SIR model, which probably most of you are familiar. And you can fit this perfectly. And the question, what is beta and what is gamma? Typically, beta is understood to be the transmission rate, and 1 over gamma, it is considered the average infectious period, okay? So here I'm gonna give you another example here. This is an epidemic here, and this is in the city of Portland. And the city of Portland, you have 180,000 locations. You have 1.5 million people moving through the city of Portland. The results of a survey that determine what people do at every single time of the day. And here people, there is an epidemic of influenza. Here people don't change their behavior. They continue life as usual. Here people wash their hands, don't hug each other very much, like Pancha and I did, things like that. So. And you see, you get the same curve. Here you get the same curve, but at a lower scale. The scale is not the same. The question is, can I fit this with the simplest model? Perfectly. And what would that tell me? Not very much, because what I want to know is how do I change the patterns of movement of individuals here, so in the case of an outbreak, I can control that. So this is why these details models give you additional information, but also how you change the patterns. You have to try methods that are not involved in the simple models, and sometimes you need bigger models. Now, on 9/11, in 2001, this was the planes that hit New York City. The world was despair, I think, shock. And many of us decided to get involved in this. In fact, we probably wrote the first book on bioterrorism that appeared in Siam at that time. And essentially, when you start thinking about the ways that people can hurt you, they're immense. They're immense. There's absolutely no way. So you can have in food, there could be problems. There could be also in toxic industrials. There could be the deliberate release of biological agents. There are trillions of things that you can do. So a lot of people have been working on this direction for a long time. And essentially, what bioterrorism was defined, the possibility of a terrorist act stresses the need for the development of theoretical and practical mathematical frameworks to systematically test our efforts to anticipate, prevent, and respond to acts of destabilization in a global community. And one of the big things that we have at our disposal is behavior when you pass information to people, whether they change their behavior or not. And there comes the challenge. How do you incorporate human behavior and the decision-making process in epidemiological models or in these kinds of settings? How do you do that? And I think we have been struggling on how to do this for 20 years, and we don't have very good ideas. We have a lot of phenomenological models, but there are no mechanisms to do that. This is a paper that I read with my Karl Hadeler, a famous German math biologist that passed a couple of years ago. And essentially, what we do is think about HIV. And when you think about HIV, there was a lot of information that we had about San Francisco, particularly the Castro district. And in the Castro district, there were 56,000 homosexually active men, and we knew everything about them because they joined and provided all the information that they have. There is a book that is really hard to read. It's called And the Band Played On, that tells you all these situations that were going on. And at some point, there was a high percentage of people with HIV. So the general idea, people tended to move. If you were homosexual man, you tended to move to this area. But if you know that there is a lot of disease, then most likely you will get an infection. Will you do it? So we wrote models of this type, okay? Maybe I will skip this. Models of this type, where you have, this is the core group. These are the people that have many partners. And this is the non-core. So this is the total population. And the general idea, right, whether you join the core or not join the core depends on how many cases of infections are. So you know that there is a lot of infection, you avoid San Francisco. If there is less infection, you might join San Francisco because your lifestyle is more possible to take place in that situation. And in that case, we wrote equations. This was the people that were outside the core group. In fact, they could attract different levels of people. This is a more general model. And this is how they get recruited into the core group. The core group is these three categories: susceptible, and these are people that are educated or vaccinated. That means that they take precautions to avoid getting infected, and these are the infected people. And this function here depends on the size of the core group and the size of the infection levels, and that can change, depends on the information that they have. So we wrote this paper. And what we discovered with this paper is this idea that if R0 is greater than 1, you have an epidemic, and if R0 is less than 1, the disease dies out, breaks out completely. When there is behavior involved, suddenly you get multiple steady states, you get more complicated dynamics, and almost everything that you think that you know about controlling diseases breaks down. So these are some of the papers, and now there is a school that works extensively on these problems. But it hasn't connected with the public health policy because it's complicated. So it's a big challenge of how to understand that, in fact, the dynamics of epidemics are not that simple. There is not just one threshold, that initial conditions matter. How do you take into account of these complex dynamical systems in order to understand, and diminish the impact of diseases? And it has been complicated because it has not been, nobody has really found effective ways to introduce these within the context of public health policy, which is what is very important. So I'm going to skip this. Okay, so now when I'm going to talk about this, this is what we did at some point. We have written several attempts to try to understand how behavior affects individuals. And in 2011, we published a paper in the Proceedings of the National Academy of Sciences, where I think we started to understand a little bit more. Now, how did that work? There is a math institute in Tennessee called NIMBIOS. It has to do something, synthesis, biological systems, I forgot. And you apply there, and they take you to this institute maybe 3 times over a few years, and then you join with a group of people, and they pay you to stay there, and there is no talks, there is no discussion. You just sit down and work over these 3 days what you're going to do. You also write a grant. In fact, we got a NSF, NIH grant out of this effort. But this is the first time that I was forced to work with a group of economists, among other things. And I remember one day, I wanted to really understand what they were talking about, so I closed the door about 11, and I said, nobody's going out until somebody explains to me this. And they got like 17 different explanations. So at one, I opened the door and said, let's go and have lunch. And it's complicated to communicate, and it wasn't going to happen in 2 hours. And this is really important to understand that, okay? So this is the general idea that we're modeling behavior, because having a more detailed information how this works is very complicated. We expect people to make disease risk trade-offs just like any other. In other words, if I talk to young people a lot, I say, if there is an epidemic of influenza and this nice boy or girl agrees to go to you to the movies, are you going to say, no, I'm not going to meet you or meet her because there is an epidemic of influenza? That's a trade-off. You have to make that decision. But there are more serious trade-offs, particularly for a lot of poor people. For example, in the United States, there is a lot of women that if they don't go to work, they lose a payday, and that might be critical to pay the rent, to do many things. I mean, it's just become very important. So let's suppose you have a child. The child wakes up and has temperature. What do you do? And I gave this talk sometimes to a very expensive private school in Colombia, and everybody said, well, we call the assistant to take it. I said, well, that's not the real world. What you do is you bring the temperature down of the child. That's what a lot of people do. And then you take it to the daycare center. And then you drop your son and daughter, and then you disappear. Then you arrive at work, and then you say, if somebody calls me, tell them that the boss sent me somewhere, I'm not here, and they called you in an hour, and you are not there, they can find you. And then 5, 6 hours later, you go, arrive at the daycare center, very apologetic. I just found out, I didn't know, I'm so sorry, but you don't lose your day pay. This is very critical. This is the kind of trade. Of course, by making that decision, right, you're introducing additional risk to the other children in that. So this is the kind of economic perspectives that we have that. So optimization models tell us about trade-offs, not just the best response. Adaptive human behavior is central to epidemiology and other things. And economics can help understand system dynamics and should not be treated as an after-fact accounting exercise. So this is one example. Now, this is at the individual level. Then the question is, how do you model this at the population level? This is scaling up that I was talking about. So here you have human decisions, how you do this. This might be associated with pathogen transmission. This might be how you assert your risk, right? But then there is a traditional epidemiology lists with transmission and disease prevalence at the population level. So how do you couple these two perspectives, the individual perspective with the additional information that is ongoing as you have an epidemic? So this is the things that we have been working on, and I think that is open. So modeling adaptive human behavior assumptions, scarcity of time, money, and other resources, people make decisions based on what they value. And the only word that I learned in economics is trade-offs. Health important, but also factors like family, relationship, sports, sources of possible trade-offs. People change behavior, the result of making trade-offs. As I said, this is the word that I like. People are forward-looking if they have an incentive to be forward-looking when making trade-offs. You can plan what you're going to do over some time horizon if there is an incentive. People take account available information when making trade-offs, but might not know everything. What we develop is a model of trade-offs making coupled with a changing risk landscape and epidemic. And this is what we call a complex adaptive system. So I'm going to show you, this is the simple SIR model. Here there is no births and deaths. And if this is a constant, essentially this is a susceptible encountering an infectious individual at random. This is the total population, so this is the proportion of infected individuals, and this is the transmission rate. So you assume you move around some community, and the proportion of infected individuals is I over N, and you hit them at random, and this is the success rate for the virus. And if this is a constant, this doesn't change, then these individuals become infected, and then some of them, after a few days, recover. So this is the simplest basic model. So no human adaptive behaviors is a constant. I forgot to slash it. Human adaptive behavior, see the result of choices and trade-offs people make. So this is the simplest model of this example. So here you have, so this is the way we're going to model and we're going to practice some Spanish here today. So this is the morning coffee narrative. Every day you get up, have a cup of Colombian coffee. My wife is from Colombia, and she's here. And read about current status of the disease and the World Cup, if you are in Colombia. Then you make a decision on how to behave for the next 5 days or 10 days or whatever, right? Using a value function, right? In other words, the utility function of what that decision will entitle to you. We don't require you to make projections, but simply assume the future is fairly constant over that time horizon. Now, after that day of activity, you will go to bed and wake up the next day to do the same thing. This is, of course, when you couple this is a high performance problem when you want to do simulations at this level, okay? So this is very important to figure that out. So let me just give you a little bit more ideas. 3 situations that we have. We have the susceptibles, people who could become sick. So they lose something if they become sick. You have the infected, people who are sick and spread the disease, and the recovered, people that got the disease and already recovered. So these guys don't have anything to lose, okay? So this is the 3 categories. Remember, this is a simplistic model. All individuals behave as if they have a single period utility function. In other words, the single period is I'm going to do this day by day. So I start day 10, then day 11. And in that period, they have this utility function. And then everybody makes their own decisions based on particular time horizon that might be 10 days. Then after 1 unit of time, I update the epidemic with the decisions that people in different states made, see how many new cases of infection, and this is another piece of information that they have, and I continue to update. Okay, so all individuals behave as they have a single, okay? So we assume that this utility function has an optimum. And we assume that the utility that you get if you are infected is less than if you are susceptible, and it is less or equal that if you are recovered. Here you don't have anything to lose. And this is an example. So you said you have a concave function, which is what economists like to do. Okay, I see, I blew it here. So now what we have here, we can model each agent's type choice as the problem of maximizing, right, the utility functions over a time horizon. Could be 5 days, 10 days, and this is a discount value based on the present value of these utility functions. So recovered and immune and infected contacts have no dynamic effect. The only things that have changes is the susceptible. The susceptibles are at risk of infection, which is partially determined by their behavior. Forward-looking individual behavior can be modeled as a constrained dynamic optimization problem, and generally, these contact rates, because of the utility functions, they're going to be different for these different types. And if you want to put more specification of how people interact, you can see that the average contact rate is something like this, weighted by the population sizes, and this is the probability of getting an infection. So I'm going to skip this because it's too technical. So in general, you have this function, and this is called the famous Bellman equation. Bt is the value at time t of being in health state H. This is the utility gain at time t by an individual. This is the health status, susceptible, infectious, or recovered. This is the contacts that they have. And this vector H is important. It counts the number of individuals in each health state in the total population. This is what connects you to the environment. And this is the length of an individual's planning horizon, and this is discount rate for present value of future utility gains. So this is the decisions that we have, and then we seek to maximize, they seek to maximize, and this is the Bellman equation that we're gonna use. And essentially what we're gonna have is that each susceptible individual is gonna address or a typical susceptible individual as stochastic dynamic programming. You set up a time horizon. Your idea is you want to maximize the probability that you don't get sick, and you see what are the decisions that you have to make that. The next day, you update. The levels of infection might be higher, so you might have to readjust the decisions to try to avoid becoming infected. So this is the way it works. And I'm going to skip these too many questions. And the epidemic model is modeled by a differential equation like this, right? So this is modeling the whole system, and this C is found via the individual maximizing, the contact rates are maximizing essentially via the Bellman equation through the appropriate choice of these functions. And what happens when you get those things? And it's not so critical. You get less severe epidemics. In other words, when people make decisions that are at risk, you get a lot less severe epidemics. So this is made. And you can see also that the time horizon, the planning time horizon, it has an optimum value. You cannot have a time horizon that is very, very long because it really doesn't help you. So this is when the infected come back on contact, you can see what are the values that you could have, and the infected behavior like recover, then you have a worse situation. So you can analyze all these studies, and then how much does human behavior matter? Policy to reduce the relative benefit of a contact, that's here. This is a baseline case, 7% reduction to maximize the aggregate social utility, 30% reduction to more greatly reduce peak prevalence. So you can make all these decisions associated with that before nobody was being able to make with a very simple model. And this is really very important because, for example, in the last epidemic of influenza, there was no vaccine. So one of the most important things that we have to address that, or in a case of bioterrorism, is to precisely take into account that. Now, so this is the simulation, the coffee narrative, and you can write this in a differential equation models. In this case, you don't have births and deaths. That would be a single outbreak. And what happens with the behavior prolongs the epidemic, reduces the total epidemic size. Obvious case confuses, invalidates the meaning of the basic reproductive number. This is another example. What will you get in general? What you get when you change your behavior? And I'll skip that. And then what happens if you have births and deaths? What happens if this is a long-term dynamics? You have a long-term dynamics, it doesn't make a lot of difference because you can see you get these oscillations, you get some changes, but eventually it stabilizes because eventually people figure out what's going on and they make decisions that are pretty much uniform. They assess the risk of what is going on forever. So this is the one kind of thing. You can see you get a little oscillations here about this, but in some sense it doesn't make any difference. But when you have a single outbreak, it can have a significant event, and these single outbreaks is the ones that we're the most interested. Okay, so we expect people to make disease trade-offs, just like any other. Optimization models tell us about trade-offs, not just the best response. And economics can help understand system dynamics and should not be treated as an after-the-fact accounting exercise. Now, I have more slides, but I think this is enough. But I'm going to address a few more points of one of the things that we're interested. One of the things that we're very interested is in the role of mass transportation. And I have several slides about that, but then it becomes too much information. And in general, we have a study, for example, what happened if in New York City there was a deliberate release of a biological agent like smallpox. And in that case, again, you look at standard models, they look at epidemics as closed populations. When you look at that, you have transient populations. In New York City, you have about 200,000 tourists that they come every day. And then the question is, if there was a deliberate release of biological agent, somebody infects themselves with the smallpox and start traveling all through the subway, what is the best way to control the epidemic? And you can't control it unless there is substantial effort to deal with the transient population. This brings us back to many interesting issues that have that. One of the biggest problems, for example, associated with the list of immigration in the United States is that people that are undocumented, they don't go to the doctors, they don't report illnesses, they don't report many changes in status. They don't go and take care of themselves because they're afraid of being deported. What this model show in an extreme case is that the cost for society of doing that can be incredibly high as compared if you actually providing some more dignified way of dealing with these issues. So this is some of the examples that we have worked, and I have worked primarily with undergraduate students, like 500 undergraduate students, graduate students. Some of my PhD students I have known since they were 13 years old, and so forth. And they are spread now across the country, and most of them are working on problems associated with this, whether it be, and I go back to the Honorable Vice Chancellor, antibiotic resistance, whether it would be sustainability, whether it would be ecological systems, whether it would be epidemiology, and all these problems have some similar perspective. I think, from my perspective, every time we're dealing with a disease, we're really dealing with some sort of ecological system. That's what we're really dealing with, some ecological system. And therefore, the theory of mathematical ecology, mathematical epidemiology, that are pretty similar, essentially deal with the world as essentially as the interaction of individuals in different communities. The same thing with immunology, the same thing with cancer. So today, it's very difficult to see any research group not to include some modeling in their areas, whether it is cancer, whether it is immunology, whether it is physiology, people involve modeling all the time. The key thing is to put mathematics at the service of the problem and not the way around. And that's one of the hardest things to do. Why? Because departments tend to judge people by a single area expertise, and people that divide themselves tend often to be devalued with respect to the kind of activity that they realize and the value of what they do. And this is one of the problems, and that's why I'm very happy because at Arizona State University, that was broken, not entirely, but to a great degree, much more than any other university. And that has allowed people to work in important problems without fear of being judged by not devoting all the time to a single expertise. And I think it's time that we reformulate universities that way, reformulate education that way, and that we provide opportunities to students to learn science by doing this. Thank you. If you have any question, I think I might have a couple of minutes. Yes.
When you take the population and the dynamics, who is infected, not infected, and do you consider the spatial proximity is also in the equations?
Not in this particular one. When you put all this stochastic dynamic program and things like that, then it becomes. But space is important. But in some diseases, let me explain you why. I just came from Arizona. 2 days before, I was in Colombia. Okay. If I caught a virus in Colombia, it's the next day is in Arizona, and then 8 hours to London, then London to here, and now I'm losing all my friends in India. The use of space is important for some diseases, but for human diseases or for trade, and we had a grant that deal with trade, is mobility and the transportation of goods at tremendous speeds. That's the problem. Now, there are areas where space is very important, like plant diseases, agricultural pests, things like that. Then that becomes very important. In general, space for in the time of globalization is very important. So when you look at the epidemics of childhood diseases in Britain, in the, I think Neil Ferguson studied somebody like that, in the Brian Grenfell. When you study this in the 1900s or 1700s, people in Britain didn't travel very far. So you could see some spread of that. But today, with the H1N1 epidemic in Mexico, started in Mexico, the next day it was detected in Canada and the United States. And in a few days, it was all the way to Japan. We don't have the mathematics to do that, but some people had studied air travel to see how that could spread. There is some beautiful papers by Juliana Rino, my former colleague at Arizona State, and my ex-student Gerardo Chawel, that have been studying this kind of impact. And the mathematics are open. We don't know exactly what is the right way to do this, so people do a lot of simulations of different kinds.
Thank you very much.
Any other question that you might have? Yes.
So thank you very much for this nice talk. I have one question which is related to this social utility, where somewhere you showed that there was a 7% decrease and around 35% for two different scenarios. Mm-hmm. So the question is, this measurement is probably dependent on the particular social utility function which is chosen, as well as different parameters. It will change if we change the parameters, or it is like optimal 7%.
Yeah. Yeah, no, you're correct. In fact, I don't think that there is a problem more important on science than how to assess uncertainty. I think that this is the most important plan. We have models, how do we assess uncertainty? Having said that, one of the things that we do is for a broad range of parameters, you can understand what is the behavior. And the standard example that I gave is I have 5 fingers, everybody has 5 fingers, and if I come next year, I can predict that everybody's gonna have 5 fingers on the right hand, and can make a perfect prediction, but I cannot tell you from that prediction why we have 5 and not 4. And that's the interesting biological question. Why do we have 4 and why do we have 5 and we don't have 4? And they have people done biochemical models for development, and they have shown that in development, when you are growing up, there is a bifurcation, and that bifurcation is odd. It cannot be 2 or 4, it has to be 3 or 5, and then now the question, why, how can you change it? So people have actually done experiments on chickens, changing the genetics to identify if they can generate chickens with 4, so that they can understand the process of physiological development. But mathematics, for example, have shown that result. So yeah, predictions in some sense are complicated, but for broad general, you can see that if you incentivize changes in behavior, there could be reductions. Now, how much it is in a specific example is difficult to tell. In the case of Mexico, H1N1 influenza, there were not only incentives to do that, there were drastic government measures like closing football stadiums and restaurants and also schools and things like that to make those changes. So there is another aspect in which that wasn't done by individual decisions, but that was done by government decisions. And sometimes that might be critically important too, and that's not considered here. Thank you for your question.
Thank you.
Yes.
Good morning, sir. Sir, I am very big fan of you because I work in the same field.
Terrific.
And listening to you is just like a dream come to me, true. Sir, my is not a question, it is a curiosity to know that. I am working on the partial fractional differential equation order to modeling the disease. Partial fractional order differential equations.
Partial differential equation, yes.
So can you throw some light on it? How much, up to how much these models are reliable and authenticate? And
well, anytime you become infinite dimensional systems, it's become complicated, particularly to connect with the stochastic dynamic programming. But in terms of epidemics, without changes in behavior in this fashion, certainly you can write the partial differential equations. But in that case, if you think at utility functions, there might be a function, for example, of age and time. And then that becomes complicated. Maybe for some particular age classes, you could assume that they remain the same, and for others differs. There are some nice way by Herbert Heathcote many years ago, where he rigorously builds models that are discrete in age and continuous in time, and then you can choose any age brackets, and then you could assume that for those age brackets of different length, that perhaps the decision-making process is the same, and then maybe this can be computationally tractable.
thank you, sir. Thank you so much.
Thank you.
Thank you, sir.
Very much.
So we really thank Professor Carlos for the plenary lecture.
I have something for you guys.
Okay. Yes.
I forgot. Yes. I have something just to give to the, because now everybody's going to be a mathematical biologist, to give to the library of your schools is a copy of this book. Thank you very much. I'm going to give it to you. So, thank you very much. I appreciate it.
I'm sure all of us are really enriched by Professor's talk. Sir, I request Vice Chancellor sir to give our tokens of love. Sir. Thank you, sir, for the plenary talk, coming all the way.
Nice day in time.
Yes, sir. Yes, sir. You have a bag, sir. Bag is there.
Oh, you have a back. Oh, that's
Yes,
better. So you guys are very well organized.
Yes, sir.
Thank you very much. This is incredible.
Thank you, sir. We'll all have a break for 20 minutes, a tea break, and then reassemble, maybe around 10:50. Right. Okay. No, break is outside. Here, we are going to reassemble here at 10:50.
nice models.
Says uncertainty. It becomes too much information. And infected contacts have no dynamic effect. The only things that have changes is the susceptibles. The susceptibles are at risk of infection, which is partially determined by their behavior. For You send me hi and your
Sairam, we will now begin the second session, and at this juncture, I would like to thank Professor Carlos for a very enlightening lecture in the morning, and also the Vice Chancellor for gracing the occasion with his introductory talk. Now, moving on to the second session, it's my honor to introduce to you all Dr. Anuj Mubai. He finished his BSc in 1997, then went on to do his MSc in pure mathematics from IIT Kanpur and completed that in 2000. After that, Dr. Anuj received his doctorate from the Arizona State University in 2008. He is currently an assistant professor of applied mathematics in the School of Human Evolution and Social Change. He is also part of the Simon A. Levin Mathematical Computational Modeling Science Center at ASU. He is also co-director of Mathematical Theoretical Biology Institute and director of the BS in Applied Mathematics in Life and Social Service Sciences undergraduate program. Apart from all this, he also holds adjunct affiliations at multiple institutions including University of Texas, Northeastern Illinois University, etc. He also held a Gates Foundation Fellowship at the Cleveland Clinic and National Institute of Health's Fellowship at the Case Western Reserve University School of Medicine. His current research includes development of novel mathematical modeling tools to understand transmission dynamics and control of neglected tropical diseases. Today, Dr. Anuj will be speaking on the topic, which came first, the chicken or the egg? He will be reviewing the studies on mathematical modeling of infectious diseases. With these few words, I invite Dr. Anuj to address the gathering. Thank you.
Hello. Yes. Thank you for this nice introduction. So you guys, all have seen the talk of Carlos Castillo Chavez. He was talking about various type of models that that we are trying to work on lately. But this title that I have chosen here, which came first, the chicken or egg, this has always been a challenging task for all of us, especially individuals who are working in interdisciplinary area. Whether, for example, my background is mathematics, so whether I should focus more on mathematics or whether I should focus more on the application that we are trying to focus on. And that is the reason I came out with this title to share some of the research that our research group has been doing, which actually which will reflect some of those aspects. Both are equally important, but some places one is critical than others. So before I go into it, I just want to give the structure of the school or the workplace that I work at. And which one is the pointer? I think this one. So ASU is the university, and I am in the department which is called as School of Human Evolution and Social Change. And as the name suggests, it is, you cannot say it is physics, it is chemistry, it is maths, or it is something else. It is a combination of many disciplines. So there are researchers who comes every now and then, actually every week, sit together for a meeting and discuss on various issues, including anthropology problems, for examples, and many other problems of a person interest. And we are actually solving a real life critical problems of today's life. And so that is a department. And then comes a center which is which is initiated by Professor Carlos Castillo Chavez, and now it's called as Simon 11 Mathematical Computational Modeling Science Center. As the name suggests, modeling, there are three major aspects: mathematics, mathematical, computational, modeling. Those three things are combined with the science. And that is what skill set are brought in the center from various, so there are a lot of affiliated faculties who are experts in epidemiology, in social science, and other disciplines who are part of the center. Under that center, we have multiple programs. There is a high school training program, which is called as Joaquim Bustos Math Science Honor Programs. So we train them in the same way as we train our graduate students. So we have high school program, we have undergraduate programs, and we have a graduate program. And actually, some that we are trying again, we applied for some last year, we didn't got funded, but we are applying again for a professional also, early career researchers, to train them into some of the aspects that we do, which is quite different than a traditional way of doing things for example, I graduated from IIT Kanpur, and Professor Ratish Kumar, I think he's here somewhere in the audience, he was my mentor at that period of time. So this is a rough structure, and in all of these things, the diversity is very important. Not only national diversity, we have females, we have minorities, we have underrepresented communities in our program, but also international community is very much represented in it. Okay, so he's Dr. Simon 11. He's a very well-known, distinguished ecologist, actually. But he works also in many mathematical problems, and if you Google search it, you will get thousands of news articles in his name. And he was our provost before, and Carlos is in the middle of this thing. So he inaugurated our center, and that's why his name appears in our center's this thing. So what do we do in our training structure? So we are bridging the gap. The gap is a very important thing, bridging a gap between what is community needs. Well, we do all these mathematical methods and we learn these methods. What can we do with these methods? How can we use it to solve day-to-day real-life problems? We have to think of, and that's one of the things that we focus on, what are the needs of the community and how we can train our grad students or our peers in those type of methods that are useful to address the current challenges. That is the main goal that we are focusing on. So if you talk about any cutting edge problems in real life, it is cross-discipline. One discipline cannot solve it. And so therefore, we need people from different departments, different skill set to come together and sit on the same table and discuss about those problems. Okay, so this is general. Let's go to, so we have two programs here. It's called as Applied Mathematics in Life and Social Sciences. Now, remember, I'm giving these things, although it was a mathematical modeling of infectious disease workshop, but I'm providing you these general framework here because environment is very critical for even describing the models, how you tackle the situations. And these all things will help you see in what environment we work and how do we deal with the small things and into day-to-day life. So we have two programs there. It's a Bachelor in Science and it's a PhD programs. And they both have a very distinct skill sets. And they are trained to the current needs of the US, for example. So for example, we in our classes, we teach how to read, evaluate, and present scientific reports. I don't think I was taught when I was in my PhD program all these things. I learned it by experience. That's a different issue. But this is all the things we teach it in the class. And that makes it a distinct flavor in those things. We also give some kind of outline of where to search jobs. What are the places here, for example? What are the websites in India that you search for a job? What are the places? I'm asking an open question here. What website do we go for searching a job, academic job, let's say? Anyone? We don't have any, right? So how do we get to know all these jobs, search jobs? Well, so these type of information, what is fake news, what is non-fake news, has to be discussed, right? And there's no one an expert in these areas, but when we discuss, there are different views come forward. And there are different decisions that we decide on, and then there is a common consensus of this area would be, this website would be better than that website. So this is all we talked about. Actually, we discuss in an environment. It's not that I'm giving a lecture, but I will discuss with my my students, for example. So also, one of the important things that we do also is we make them students, PhD students, are part of empirical data collections. So one of my students actually did, for example, surveys to collect the data for their models. So we are not now depending on others to collect the data. And many times we build a model, we do analysis, and then we look for a data, which is kind of going opposite of what mathematical modeling is about, right? Mathematical modeling is about asking a real life questions and then coming backward to think of what is the best model that you can think of and work upon those by your mathematical skill set, right? So those are the things. So data collection becomes a very critical role in our group. Also, one thing which I never had a chance before was a mentorship. We never get a chance to have a mentorship in our graduate program. I didn't got it. So I think that is very, very important, very, very critical. How do you train someone who is less skilled than you in an area that you are expert in, for example? So those are very critical aspects, and this is, and I will give you an example how do we do it in few slides ahead. Also, this is typical. This is all we learned. We all do these things, current methods in mathematics and computational science, and we know about those methods. But these are equally important, and this all things make us a comprehensive person in that regard. So how to read and search for jobs, how to write effective reports, how to present. An example of survey we actually try to train in my course. I actually train how to write surveys. You know, if you ask you to write around a question for collecting a data, you know, each one of you will be writing a different question for it. And if you give that question to people, they will respond in a very different way. So there is a very specific way to write this specific question. For example, if you are asking, what is your future plans of in your area? And you want to collect a data for that. So you have to write this question in a very, very particular way in order for you to get a right kind of data. So Professor Grillo is sitting at the back, and we are working on a problem. We are doing currently a survey at Arizona State University. We are collecting data for studying the burnout rate. Many students are right now overwhelmed with the workload, and they don't know how to manage these things. So we are carrying out this study at Arizona State with his help, and we are working with psychologists also, and to find it out to what extent this is a problem first, and if there is a problem, what social behavior factors affect those things. Now this is a relevant questions to my campus, for examples. Okay. So, and this is also an important point. Once you have the data, how do you extract a good information from it? Because data has multiple information. Not all information is as useful as others. Now, there is something that is very important, and I don't know how many of you heard about Mr. Sonam Wangchuk. I think Mohammed is sitting there, and he knows about him. He's from IT Mandi, and Sonam Wangchuk was visiting your campus, right? Mr. Sonam Wangchuk, he's an educational reformist in India, and he's a national award winner. He is in Tibet, right? He's in Tibet. And Ladakh, sorry, Ladakh. And he is, I got to know about him through Kaun Banega Crorepati. And he was interviewed by Amitabh Bachchan, actually. And the interesting point was he made some interesting point, and that just catches my attention. One of the things he does there is he is passionately involved with solving local problems. That is one thing. And when someone is passionately involved, they figure it out, the resources for it. For example, what he did was there were a lot of, these are untrained people, right? And so they were performing very bad in schools, right? Because they were not doing this, because the standard was same as we have these boards, like, you know, high school board, 10th or 12th boards. And they were not doing very good, and they were getting failed in the classes, right? So these classes, when they were getting failed, what do you do with that? Do you throw? Well, in Ladakh, almost 90% will have no training before. So you will just throw all 90% of the people? No. So what he did was he started something, he called it as a University of Failures. And the idea was, okay, they might not be performing very good in mathematics, but they might have some other interest other than mathematics, for example. And just let's develop those interests in that person. Okay, so that's what he did as one of the things, and that's how. And there are many things he does in that. And another problem, he uses some scientific expertise and collaborate with ISC Bangalore, for example, and other institutions to resolve some local problems. There is a water shortage, for example, in the winter season there. And so I think you guys should look for this thing, and Mohammed can share the link, actually, if anyone wants to talk about it. Now, why did I mention this thing? Because I realized that we do something similar, if not exactly. So we have, in our programs, we don't give. My interest is in neglected tropical disease. I don't give the problem, okay, you work in this neglected tropical problem. We ask a problems, what interest is the student interest? For example, Mugdha is sitting here. She wanted to work in gender disparities and gender-related aspects. And so she's working in a problem like this. Caesar is sitting there, and he was interested in resolving waterborne infection in Ecuador. And so he's working in that problem, for example. So what their own interests are coming into their research topics, and that makes it a more flavorful. We only help them to guide in a proper questions and proper way of doing the dissertation and progress smoothly in their dissertation program. So most of the projects are student driven. This is very, very important, student driven. Second thing is it's a multi-layered mentoring program. So many times we are kind of hesitant to go and approach our faculty. When I was in my undergraduate program, I had a very difficult time. But I could easily approach to my graduate students, for example. So we have multi-layered mentoring system. We have graduate mentors, graduate students who are mentoring undergraduates. And we have early career researchers, postdocs, for example, mentoring graduate students, and so on and so forth. So there are multi-layered mentoring systems, and they can approach to any level of these mentors. Okay, so this is general. And one thing also is they learn from their peers. They learn more from their peers than from me, for example. So every lab meetings, they train each other in the skill set that they know about or they are already trained in. And that is a quick way of learning many of those things which you will never know if you will do it by yourself. I mean, you will not be able to expose that wide variety, basically. Okay. So, for example, I teach a course which is called as Modeling and Simulation in Global Health and Neglected Diseases. Just to give you a flavor, there are speakers. I have it on Skype. They live stream their lectures from remote areas. For example, Swiss Tropical Medicine has a CDC, Center for Disease Control at Peru, for example. Professor Grillo also was doing a lecture in it. So I have my collaborators in different institutes who are talking in these courses, live streaming. I'm not an expert in neglected. I've learned it over experience. But these are expert in it, and they can give a first-hand information on these type of topic. And that's why I invite them to come and give a talk through live streaming through that. And our students actually do a surveys, and this is a flyer for carrying out a survey at an ASU campus, for example. Okay, so most important thing that we focus in a viable research question. What is the need, community need right now? That is a very, very critical aspect. Mathematics is a tool that we work on, and of course, your tool, you need to know about it, but then you have to address a viable research question. That is what our focus has been in our programs. Okay, so just to give you an outline of it, students are across from disciplines, different disciplines. They, of course, receive in quantitative mathematics training, but they not only receive mathematics, they receive statistics training, they receive computational training, but they also are allowed to work with someone in other department, for example, biology department or in social science department, or the choice of their interest, basically. We help them to collaborate with other faculties. And many times, those other individuals are part of their dissertation committee, for example. So as I was talking about, there's a flipped hierarchy. The project ideas come from the students, and we just guide them. So we are not aware of those ideas many times, but those applications. And we basically help them asking a logical questions, and that's how they design their viable research question. Okay, so I don't want to bore you all, but some of you might not, because I was not aware. I thought of what I should give a lecture here, but I thought many things I was not aware of when I was in my undergraduate or graduate program. So why not just expose those things that you would maybe knowing about it, but maybe not. So so PhD dissertation is usually guides your positions. What topic you work on, what application you work on, actually helps you decide what position you should go for. It's not everything, but it's a good start, and you have good tools in your basket that you can work on various things. Okay, so now in US there are 4 different types of academic institution. I'm guessing here also there is 4 different types So primary research academic institution, ASU, Arizona State University, is primary research and teaching academic institution where 50-50 is given weightage for teaching and research. and teaching academic, mostly teaching that is preferred. And there is partially academic institution. For example, I worked for a Cleveland Clinic in Ohio, which is one of the top-notch hospital in US. And there are departments, but they also have patients. Okay, so they are teaching courses, but they are also handling the real-life problems. So they are partially academic institutions, for example. And the requirement for the hiring in these things are very different, for example. So just to give you what are the requirements for it, so when research and teaching academic institution you have to go through phone and on-campus interview. Phone interview is separately. If you get shortlisted in that, then you go for an on-campus interview for 2-3 days. And then the course load that you teach on a daily basis is 2 courses per semester. So 2 + 2 means 2 in the fall and 2 in the spring. And then there is a research expectations because it is research and teaching academic institution. You have to know where you are applying, for example, there. And roughly around 15 to 20,000 is the capacity in US of the students that constitute that type of institutions there. Then comes the primary research academic institution, which is phone and on-campus interview, same thing for getting hired. But then the reduction in teaching load is very reduced, sometimes even 0 and 1. But you are expected to write a lot of research grants, and you have to expected to bring a lot of grants for it. Okay. So this is the department building. I should have had a different picture, but my department building. So the application material, this is very important. You know, we had this forms. This idea came to me because we have this Google Forms where you were entering these data for this workshop, this particular workshop. And I saw CVs of some of you, actually all of you, who applied there. And something I noticed in some of the cases that the CVs are very different in the way we focus on. And I think it is very important how you structure your CV because it captures what is the essence of your background in a much good. Remember, the people that are evaluating at any stage do not have much time. They are very busy people. So they would like to see these things very quickly and very fast and to get your idea of the individuals in just few minutes, actually. And unless there is some reason why they want to go details into it. But these are the main things that the cover letter is very, very important. Cover letter is a gist of everything, teaching, research, service. And these two things are also very important in research statement and teaching. So we spend a lot of time in writing these things because this gives a flavor of what type of background an individual have. We can quickly make it out from the first paragraph whether a person has really spent much time in writing those things or not. Is that the same procedure here for getting hired in academic position here? Is the same material? Okay, so our center and school and programs at ASU are interdisciplinary modeling areas. So as I was saying, my department consists of all these areas actually. And we have multiple programs which kind of feeds up, which gives you a mentoring, students to a mentoring abilities, because the undergraduates are training graduate students are training the undergraduate and so on and so forth. I hope it is not boring, by the way. So please stop me, I will rush to the next slides. And okay, so these are some of our recent graduates. For example, he graduated, his name is Carlos Toro. He graduated in 2009. He's a VP of JP Morgan Chase Bank, for example. Daniel Rios, he graduated in 2010. He was earlier in Goldman Sachs. Now he's working for a government agency that he can't tell us. It's a secret US government agency. And David Murillo, he's working for American Express. He graduated in 2012. Kevin Flores graduated in 2009. He's a professor in personalized medicine at North Carolina State University. This is actually for him, they made the department. I mean, they were thinking of that department, but they hired him. That was the first few set of individual hired for that department. He was one of them. She's working for Romary Morales. She graduated in 2016. She's a research scientist at Pacific Northwest National Laboratory. And Beverly Gonzalez graduated in 2015. She's a mathematical statistician at United States Department of Veteran Affairs. So the reason I'm showing these examples, and there are many more, is that we are developing their skill set, and they are going in a very different disciplines of their own choice. If they want to go in academia, that's well and good, but if they don't want to go to in other areas, that's also good. And many of the institutions like US Department of Veteran Affairs, they are doing research also. National laboratories are also doing research, just like the universities, for example. So we also organized, this is one of the example of the workshop, but we also organize workshops at various places. So I was there in Portugal last year, invited by Professor Grillo, which was very, very unique in that, say, there were people from many different disciplines to talk about. But also, in 2019, we are organizing a workshop in Banff. Banff is one of the beautiful places that I have traveled. And it's really gorgeous. It's a heaven actually on earth, I feel like. There's a glacier there. There's a handful of people. It's in Canada. It's in Calgary, province of Calgary in Canada. And we are organizing it in 2019. And it looks like this. Look at how beautiful it is. And there is a mathematical research station there, and they fund to organize a workshop in Canada and US. There are a lot of these organizations which funds those funds. So we are organizing there, and there are scientists who are coming there for that workshop, social scientists, biostatisticians, psychologists, medical doctors. It's very interdisciplinary, although we will be talking about mathematical and computational modeling aspects of it. Okay. So Professor Carlos Castillo Chavez started this Latin American consortium. Latin America is South America, Central America, and some parts of Caribbean. That constitute the places where Latin is spoken. And so there are lots of members of this consortium, and it was initiated by him. And this was in El Salvador, this is in Colombia, and it's Mexico and Ecuador. And every year it is different. We have a meeting with. But this is the workshop in that direction, and I wanted this India to have some type of consortium also. And that's how I'm just exposing you what we are doing right now, and we are not only restricted to US. For examples. This is the workshop that we organize every year. The 5th one just culminated. It was in Colombia. And it's an international workshop. Every year the focus changes. Now, the focus of it changes, but we have individuals from mathematics, statistics, computation, but also from economics, also from medicines and other areas, depending on what is the focus of it. Now, we also make our presence felt through social media. It is very important in nowadays. Well, it is a balance that we have to maintain in terms of how much time we want to spend for our social aspect versus professional aspect. And that is always a delicate issue. So we have a Facebook web page. For example, there are a couple of Facebook. This is one is on the top and the other one is on the bottom. And anyone is free to join those two groups, by the way. There's no restriction in that. So please do that if you are interested in something like that. And also we are on the Twitter, for example, and we regularly feeds the Twitter feeds. And as we are saying, this workshop will be also in the press release very soon. So one of the programs that I co-direct is called MTBI, Mathematical Theoretical Biology Institute. It's a undergraduate research programs, and this is the group from 2018. Let's see, where's Professor Carlos Castillo Chavez is here, I am here, and I think Dr. Debroy was here, in the MTBI a few years ago, and Mugdha and Caesar was also there a few years ago. And so we had some, Professor Sheshiyar was also part of that, and he's a regular visitor of our center. He's a faculty in our center as well. So he is part of many things there. So let me say, this is an undergraduate research program, but you will be surprised to see how they work. Let's see. There are around 130 PhDs. So we had 500 graduates from this. This is a 2-month summer program. 500 up till now have graduated through the summer programs. 130 of them, these students were not really interested in mathematics when they joined this program. We took only those people who will not go get these opportunities. We typically selected from the smallest school with few resources to come and visit us, and we pay them for doing that. We had flights, we have hotels, we have food, we have a stipend for them, and it's a good amount of stipend for them for 2 months. And they come there and they kind of learn these mathematical modeling tools and the way we teach these methods to them. So there are, every year there are 200 people, 200 students or more, like 200 to 300 apply for just 20 spots, So it's a very cutting edge in that regard. Of course, not from India standards, because we get lots of application in India. But from US standard, it is a huge, actually. In this, one of the important things are homework and the group works are evaluated, not graded. There's a difference in evaluation and grading. We go over their steps, but we don't give 100%, 90%, 70%. We don't give that, or you fail or you pass. We ask them to redo the homework if they have skipped some of the steps. That motivates them, or that motivates them to ask their peers to learn and do these things again. And that's how they learn it very fast. And again, the topic of the project that they work on comes from these undergraduate students, first time seeing these mathematical modeling skills, first time seeing the application, but they all have their own ideas. You know, one of the group started by thinking they want to solve the world poverty, which is kind of a very big problem, right? But we help them to guide into smaller and smaller problems. And there is a 1-week-long session where around 15 to 20 faculty mentors that sit in the room, and these research group starts to talk about their research ideas. And we help them on a viable research question of the problem of their own interest. That is important there. And so we form the research community. The website, the Twitter or email, the community is built by that. We don't just leave them in the summer. We're done summer and they're done. We involve them throughout. Once they are part of MTBI, they remain part of MTBI throughout. They start their session. This is 2 months long. They start their session at 9 a.m. in the morning with the lecture 1, lecture 2. By the lunchtime, they have a student problem. This is done by the graduate student problem session. Then they have a lunch for 1.5 hours. Then they have a computer labs where they are learning many different softwares, not one. They are learning Python. They are learning QGIS. Have you heard of that? QGIS? It's a geographical information system, for example. They are learning NetLogo, which is an agent-based modeling technique, softwares. So there are many softwares they are learning which are easy to model, use in the models and apply. And then they all sit, faculty, graduate students, undergraduates, they all sit in one room and eat together dinner, which is, we call it as a mentor meal. And then 8 to 11, they have a homework from the morning lecture, and they end around midnight. We don't force them. They work, and they have to teach each other if they have a problem. They work in a group. So they are doing these things 6 days a week, 2 months. It's for undergraduate students who are not exposed in this environment ever. So it is very challenging to them, but they do it fabulously well, and they work because it's a community we are building. We are not teaching them as a lecture, for example, and that makes a difference there. And it's a very successful program, by the way. It has got 2 presidential White House awards so far. So let me go. How many minutes do I have actually? Like 10, 15 minutes? It was started at 11, right? 11:15. Okay, so I think I will not. I'll go to my work now. So modeling trends in infectious disease. Actually, infectious disease has a very long literature, although we never get a chance to go over back that much of literature. And it is very important to know the difficulty that other researchers have faced in the past. So it starts from John Grant in 1620, when they talked about, when they used the smallpox was the big problem during that point of time. And they tabulated the mortality of smallpox. So the model there was just the table. Well, we talk about models just by differential equation. Every field, the model word is used in a different way. But their idea is to make the complex system. Oops. I moved my hand a lot. Thank you. Thank you. So the idea here in the modeling is to take the complex systems and how do you make it concise that a human mind can understand. That's the idea of the model. It could be a written words, it could be equations, it could be a flowchart diagram, or it could be something else. Okay, so it started actually in John Grant by 1620, and there has been some pioneer work by Daniel Bernoulli. There are many theorems on that, for example, and many of them. William Farr also talked about some stochastic model, for example, and so on and so forth. Carlos was mentioning about Ronald Ross and Cormac McKendrick, which actually transformed, and they the way the people were modeling, in the sense that they introduced the topic of tipping point, when the system tips from in mathematical terms, when the bifurcation occurs. And that is what the role of this 3 pioneers have been. Now, we actually work on complex systems in some sense, because the problems where even infectious disease itself is very complex in that regard. So we use, you see the evolution of different methods over a period of time. There was optimization and probability game theory. There was certain types of models that were used in 1970s, but now they are taking roles in network science, and they are using models from different disciplines to combine the new methods. Right now, it's not that one size fits all. It's not that the one method, this is the most advanced method and you can use it everywhere. It's not that. But this is just showing what were the community needs and over a period of time how the methods are developed. Okay. Okay, so these are some of the evolution of the methods there. Dr. Debroy and I just published, I mean not just, but it was published in I think 2017, 16? Last year, 17. It's emerging themes in epidemiology. Now, it is very difficult to, we are mathematicians, right? So writing down the story for a non-mathematical audience and publishing it in the epidemiological journals is very challenging. Mathematical journals, we can publish at any time. I would tell you that. But these ones, initially, we got rejected many times. But now it is fine. I mean, we learned their tricks. But in this paper, what we did was we did a comprehensive review. One of my area is Kala-Azar. How many of you know about Kala-Azar? Anyone? Kala-Azar? So where are you from? Which place? Here? In Bangalore? But Kala-Azar is not here though. No? It's in Bihar, right? So where are you from? You're UP. But UP also has it. So Kala-Azar is scientific name is visceral leishmaniasis. And it's a major problem in East Uttar Pradesh, Bihar, and West Bengal, and actually Bangladesh, Nepal. And it's Bihar is one of the highest prevalence in the world. And it's a neglected disease because it's a disease of poverty. And so not much attention is given to it. And so I work on this. I work with Indian Council of Medical Research here in India. And I collaborate with Rajan Memorial Institute of Medical Sciences in Patna, you might know about it. And also BHU has a clinic in Muzaffarpur in Bihar, BHU School of Medicine. So I work with both of them, and BHU is Banaras Hindu University, right? So and to collect the data and to go and see if what data we need for that. So what we do we reviewed many of our studied and see and collected the methods and the data set that we are using in those, what data sets are needed in those type of methods. So for example, there were climate models where we're using meteorological data. Now there is no differential equation type model. This is a time series model. It depends on what question you are addressing that you have to choose the methods here. Right, so this is what is explained. I would strongly advise you to actually go and see if you can get a hold of this paper. If not, send me an email and I'll send you a copy of it. But this is a very good written paper which reviewed in a more in Indian scenarios, what are the challenges from the modeling perspective. So let me give you some example from my study. So one of the study that I work was on HIV transmission, and every study that I will present here, I have few examples of it from my own research. I will talk about research questions, the viable research question, which are critical here. So in this was the work we were doing in 2011-10 around that time, and it was on pre-exposure prophylaxis. This is a kind of vaccination. Oh, it's not vaccination. It is a pill that if you take it, you will not get HIV. The problem with HIV is that person who get infected often get delayed in reporting, and therefore these viruses goes inside the body, well hidden inside the body, and you can never wipe it out. But if you go in a certain window period, which is few days treatment, then you are cured of HIV. For example, healthcare workers, by accidentally when they get infected, they take these pills and they get immediately cured of that thing. So that is what is a problem, that window period is missed. So pre-exposure prophylaxis was a pill that were being tested in South Africa by a research group in University of Philadelphia by physicians. Some of the physicians there in South Africa was the largest prevalence, by the way, that time. So we wanted to see, so ART, where is ART? ART is antiretroviral treatment. Antiretroviral treatment is the treatment for HIV. PrEP is also a medicine that is the same medicine given in the PrEP. But you take it as a regular pill if you think that you will get that HIV, for example. So the question that we are addressing here is if you give more medicine in the population, so you are wasting. So PrEP, for example, you are giving a medicine and some people may not be infected and they will be taking it, right? You are giving more medicine in the population, it will cause more resistance cases. Think of that. You have developed the drug for 60, 70 years. You don't want to waste that research by creating more drug resistance cases, right? So the question now comes, if you want to implement the PrEP, whether you are getting benefit out of it more versus drug resistance or not. So that you have to evaluate using mathematical models. Okay, so this is what the such study was about, and we built up the model, and this model was coupled nonlinear differential equations, HIV model differential equations, as many of you might have seen it, but think of the complexity it is involved in. Now, it was not the choice of us. We mathematicians don't like complex models. We like simple models so that we do mathematics on it. But this was, since I was working with the medical doctors, they wanted to do a lot of detailed study on that. And therefore, they have male and female in that. There are sexual activity level in that. There is whether PrEP is there, ART is there, and there is infection stage. There are different infection stages at which you can give these type of treatment. And there was drug sensitivity. There were 2,300 differential equation coupled into it. Think of that. Can you do any maths? No, you cannot do. But it is addressing the real life current challenge. Now, that was the need of this problem. That doesn't mean that I would suggest you guys to do all these problems in that manner. But in that way, it was needed. Now, we were running the clinical trial, so we had all the data in hand. And that was the best part of it. And so we could make it more complex model in that sense. Okay, so what was the result? The result was art and prep is combined together has a more beneficial role than each one of them separately. Okay. Second was they were thinking this prep will introduce more drug resistance. In fact, the treatment, regular treatment, was misused so much that turns out mathematical model was telling us that the treatment itself is causing the drug resistance more than the prep that we were trying to implement. So this is not a natural answers to some of these problems. You can't get these things without some kind of mathematical structures or understanding over a period of time. This is study 2. This is published in Acta Tropica. It is very pioneered journals for studying tropical medicine, basically. And here, the idea is these are Trypanosoma cruzi. It's another this is a pathogen which causes Chagas disease. How many of you have heard of Chagas disease? Anyone? Chagas disease? It's common in America, but it's a neglected tropical disease. Neglected means not heard much about it. And here the problem was we were modeling raccoons and wood rats, and these are vectors. These are vector-borne disease. That means these vectors bite, and that's how this infection is spread. So the problem here is we were modeling in the wildlife these things because people, when they go to these wildlife, that was the source of the reservoirs, and they were getting infected while going to this thing. So we wanted to see, but there was no data available for the wildlife, right? What was the data available? The data was available was ecological. It was the life cycle data that was available, but the contacts, the transmission data was not available. So how do we generate these data, or how do we find this data? So then what we did was we used a simple agent-based models, not simple, actually it was very complex. And we generated, used these alternative source of data into this agent-based model to identify what is the transmission coefficients in the wildlife. We had a habitat structure there, we had a density structure there, those other sets of data. So this is, the role of mathematical model is not only about generating hypothesis, but also for collecting data. That is what I'm trying to say here, using another source of data. Now, this is not empirical data that you are collecting from the field, but this is model under certain assumption, this is the data that you are collecting. So again, the tool was agent-based model, not differential equation here. This third one was in India, and it was published in one of the top-notch American Journal of Tropical Medicine and Hygiene. It was done by one of my PhD student, Kaushik Gaurav, in 2013, I think. So this was with Rajendra Memorial Institute of Medical Sciences in Patna. And there they talked about that we are spending, this was the question came from them. They were saying there's lots of money that we are spending in Bihar, and the way we distribute resources there in Bihar are based on counting number of people in each district, and that's how we allocate insecticide. Now, this is a vector-borne disease, so you need to spray insecticides. So they count number of people, and that many kgs of insecticide is distributed in each district. Now, note one more important thing here is that this is a vector-borne disease, and in Bihar, if you have gone, in fact, in anywhere in India, there are a lot of kettles. Have you guys seen that? A lot of kettles and kettle sheds in the same town as the people are living. Now, these biting are proportionately distributed in these kettles. If we don't take into account those things, or we don't take into account the places where these kettle sheds are, or how many are there, we are kind of overlooking a major point because many of these disease is spread by sandflies. And sandflies are in these kettle sheds. They are found in kettle shed. we are wasting our resources if we don't focus on those aspects. So what we gave them an idea about, we built a model using spatial structure where we had kettles, we have humans, we have kettle sheds, we have housing, and we wanted to see how we should distribute the resources with the same budget in hand. Okay, so the present allocation was 37 grams per person. That's how they were allocating it. And they were only focusing on only human earlier. And we used optimization problem in it. And we figured it out that if you use DDT, the amount is so less per person, but you have to also distribute in the kettles. You have to count the kettle also. So you have to need the other data set also for distribution. No other data set. And for deltamethrin, which is another insecticide that is commonly used in that area, those numbers are different. Now, and you have to cover 4 times the number of kettles to optimize the availability. And you will achieve 20% more reduction in cases. So this was the idea that we provided, and they are now implementing it actually in Bihar. So we work with the Bihar Society through ICMR. What is it called? Bihar Health Society. I think it is called Bihar Health Society. Okay, study 4 is about Zika. Was one of the study. Let me ask again. How much time do I have? Oh, we are short. Okay, so this is the last work. So let me wrap up with this. This was a Zika outbreak that started in 2015 in Colombia, and it was growing. When the outbreak happens, the data is very underreported. But it grows exponentially because the interventions are not yet implemented. So how do you find out what is what is the intensity of the growth of the infection? And we were one of the few ones in, when the outbreak was going on to say something on those lines. And we predicted it is and of course we use a mathematical model for it was a rate of exponential rise is this much, rather than many other studies which were predicting for that. This was specifically for Barranquilla, Colombia, because we could get some data from there. So I hope I will stop here. Yeah, I have a few more studies, but I will stop here. And I hope it was interesting enough in that regard. And if you have any question, feel free to ask me. Thank you.
Thank Professor Anuj sir for his talk. We thank Professor Anuj for his talk. Sir, our token of love, sir. No, we have back for everyone, sir. So. If you have any doubts in the afternoon, we have hands-on session with being handled by Anuj sir and Professor Seshia, so maybe doubts will take that time. Because of lack of time, I think doubt session will keep it in the afternoon.
Om Shri Sai Ram, and a very good morning to all of you present here. I have the pleasant duty of introducing the next speaker, Professor Padmanabhan Seshayar. So sir completed his master's from the Birla Institute of Technology, Pilani, and then he did his PhD in applied mathematics from the University of Maryland, Maryland. So Professor Padmanabhan Seshayar is a tenured professor of mathematical sciences at George Mason University, and he serves as the director of the STEM Accelerator program in the college, as well as the director of COMPLETE, Center for Outreach in Mathematics Professional Learning and Educational Technology at George Mason University. Sir's research interests include computational mathematics, computational biomechanics, STEM education. So during the last decade, Dr. Seshaya initiated and directed a variety of educational programs, including the graduate and undergraduate research, K-12 research, and teacher professional development. So in addition to his research accomplishments, Dr. Seshaya contributed extensively to teaching and won several prestigious awards, including the President's Excellence Award in Teaching, which is the highest award for teaching offered at 2 different institutions, the Faculty Mentoring Excellence Award in 2013 and GMU Alumni Faculty Award in the year 2014. It's a pleasure, sir, to invite you to speak as a keynote speaker in this workshop.
And it's that, yeah, just full screen. Okay. Well, thank you very much. And I know that I'm standing between you and lunch. So I want to make sure I will go till maybe 12:30 or 12:35, and then we can continue in the afternoon session. So first of all, thank you very much for giving us the opportunity to come here. This is a great pleasure to be here, and also to have some of the colleagues that I have worked with, and I think and it's always good to see a collection of faculty, students, parents, so it's a diverse audience, so that's actually great. So I'm going to be building on what Carlos and Anuj talked about, but it is going to be more on the focus on modeling, focus on competencies we need for modeling, and then some frameworks and some that you can use that are available or countries are coming up with that you can use to think about problems and all that. So the pictures here actually tell some of the stories that I'm going to be talking about. If you are wondering why I have this picture here and what does this have to do with infectious diseases, I will tell you, I will make you imagine what this picture is, but I'll tell you how this fits in, how this picture fits in. Of course, this is probably easier to think about as for an infectious disease. So, and of course, I'll tell you stories about those things also. So, about me, that's me in my office, but I actually work with different types of stakeholders. Right now, I serve as the Associate Dean for the College of Science, which means I work with 11 departments, mathematics, physics, chemistry, geology, and so on. And so I work with all the chairs, the faculty, curriculum, research, and all that. But this is, for example, working with a group of specific challenges in defense. So when they come with problems in the field, so this is a group of people that I work with every year. Undergraduates, my favorite group of students, undergraduates and graduate students, and another favorite group which is teachers actually. So this is something that I've started doing a lot. I actually work with ministries all across the world. So, and it turns out that something I'm going to talk about will go before undergraduates. So I know that you've seen the graduate version, the postdoc version, the undergraduate version. I believe that research should start in schools. So, much earlier. So, and I'll tell you about these programs and all that. This is taking the programs to the White House and all that stuff. And this is where I work with younger kids. This is the country of Suriname. And believe it or not, 1/3 of the country is of Indian origin. The vice president is Indian. The country is the smallest in South America, landlocked between French Guyana and English Guyana, and bordered by Brazil. And Brazil speaks Portuguese, you have French, you have English, and they speak Dutch. When you think of South America, you're thinking Spanish. None of them speak Spanish. So it's a very interesting place where you have lots of diversity also, and lots of interesting challenges also. So I want to make sure you all understand that we are all trying to do big challenges, big problems and all that stuff, right? And then we are all trained in a certain way. We are trained to beat exams and do really well and all that stuff, right? But then there is some basic competencies that we need to understand, that when you are about to solve a problem, first you need to understand what is the difference between a problem and an exercise. What do you think is the difference between a problem and an exercise? What do you think? Anyone? What's the difference? Yeah? Anyone in the back? Exercise already has a solution, and problem could be open, okay? So because I'm standing between you and lunch, let me demonstrate, okay? Everybody open your hands, please, everybody, straight. Put your hands straight. Put your right hand on top of the left hand. If you didn't know, this is right, this is left, okay? Turn your hands completely. Put your fingers inside. I want you to move your thumbs. I want you to move your pinkies. I know that many of you here are, graduated from top schools. You are deans in top schools. But I want to teach you something very simple, okay? Do what I'm about to do. Do not open your hands. Try to see if you can turn and leave. Oh my God. This is what I call as the first competency, failure. Appreciate failure when you're solving problems. 90% of you failed here today. You were professors in mathematics, professors, deans in different institutions, students, but everybody failed. Super important competency to understand. When you jump into challenges like this, you're going to fail. And you have to accept failure, so put your egos away. This is problem solving. It's not a joke. And I know that you're all now trying this. I'm not going to tell you how to do this, okay? So what I demonstrated was an exercise to me, a problem to you. Because you don't know the solution. I know the solution. Is that clear? And that's how the world goes. You solve one problem in a disease dynamics problem, out comes another problem, right? So it becomes an exercise. And so you have to really understand that, wait, am I good at exercises or am I good at problem solving? And that's the unfortunate thing that many people don't understand. Okay, so when you define the problems very well, it is like, can I make this into an exercise? That's the challenge. So modeling is interesting because, it allows you to start off by observing things around you and then trying to understand, okay, what disease is going on or how is traffic going on and all that stuff. And then you kind of make a theory to say like, to go from this location to Parthi, it takes like 2 hours. You just make some theory and then you come up with some models. You come up with some equations to say, okay, distance equals rate times time. And you write a formula. And then you try to find out, okay, at what speed should I drive to get there? And then all of a sudden, one accident stops the whole thing. All your model is completely wasted, right? So it's a very simple thing. So, but in those models, you have these parameters like rate, how fast should I drive, and things like that. So you got to describe those things. And then you do your analysis, and then you try to simulate it, and either live or on a computer demonstration. And then you validate it, which never happens with Bangalore traffic, by the way, okay? Whatever you come up with, the model is going to fail, okay? Absolutely fail. So, and then of course you predict, how much time it will take for me to go from this place to that place, or how this disease will spread. So this is where the whole predictive analytics and all that. And then does it come back to reality? So this is kind of a big cycle of modeling, for example. But I want to give you a very simple message here. And I want to go back to high school now. Okay, so I'm going to start from high school, and I want to see, because many of you are probably fresh from high school, coming into college and all that stuff. I'm going to ask you a very simple question. Okay, your teacher asks you to look under the microscope, and you have a petri dish. In the petri dish, we are talking about infectious diseases, so obviously bacteria and virus is going to play a role, and the bacteria is growing. How does the bacteria grow inside a petri dish? Does it grow in a circle, or does it grow in a triangle? Or does it grow in like a nice shape? Not really. It's going to grow in some potato shape, right? So how are you able to tell me that there is 100,000 bacteria? I asked this simple question to chemistry teachers. They said, well, I put this into a machine. I said, what machine do you put it in? Oh, spectrophotometer. I said, what does the spectrophotometer do? It just gives me the bacteria count. And that's about the knowledge that most of the people have. They don't know what the spectrophotometer does. How is it actually calculating that number? And that's where the lack of knowledge is. Textbook knowledge does not get you to solve big problems like this. The textbook knowledge knows how to put that dish into the spectrophotometer, take some number, and then you are an expert at it. Unfortunately, that's what we are producing right now. I can produce machines instead, right? So the problem is, and the world is changing. We as faculty are not teaching to students who are consumers anymore. They are producers of information. That's very important to understand also for faculty. Okay, that message was for faculty. So the idea is, if you have like something like this and you have a potato shape, I will ask you a simpler question. I ask you, what's the area of that shape? I can give it to several high school students. Do you know how many people have struggled on this problem? Not even making a guess. What could be a good guess? Somebody give me a good guess. Just not a number, but how would you solve this problem? I'm asking you a very simple question. Petri dish, inside is an area. What's the area? Want to take a wild approach to doing this? Guess what? If you ask the teachers to do this, high school teachers or middle school teachers do this, they have the most fascinating and the simplest way to doing this. Do you know how they'll do this? They'll put a graph paper on top of it. And they'll put a graph paper on top of it and they'll count 1 square, 2 squares, about half a square, that's, I can say that's 1 square, this is 3/4 of a square or something. And they'll say, oh, it's about 5.5 squares. And they can find the area of a square and then they can say, hey, this is this much. That's a very educated guess. How do you make this better? What do you think? This technique, this classic paper technique, how do you make this better? Take a graph paper that is much smaller, right? Take it smaller, take it smaller, take it smaller. Wait a minute, what are we teaching? Something called Riemann sum in calculus. Unfortunately, we never even make those connections. Riemann sum, we just write some big sigma notation and then teach. But this connection is where you really understand, wait a minute, that tells me how to find the area of the bacterial, I can find out this thing. But even better, I can now push you. I can push you and say, wait a minute, so this is something I did it with 3rd to 5th grade kids, okay? Here's what I did. I asked them to draw a big circle and this potato, and I asked them to throw a chalk piece on the board. So they're throwing chalk piece like this, right? And one person is throwing chalk piece. They're throwing 13 of the pieces. 6 of them fall inside. And then I asked them to take a ratio of 6 out of 13. But that's just a ratio of what? 6 dots out of 13 dots. That's a fraction of what? Of the Petri dish. What's the Petri dish? Oh, finally, you know something, pi r squared. Now you're back in business because you know a formula, right? So this is what I'm saying about modeling. But this is not exact. So how do I make it exact? Well, the kids love it. What do you ask them to do? Keep throwing chalk pieces on the board. So they throw chalk pieces on the board. So they throw more, 20 out of 41, they throw more. And then finally, they're going to get an answer that's super good. And that's what modeling is about. And when can I teach it? In 3rd grade, in 4th grade, 5th grade. We don't do that well. In 3rd grade, 4th grade, they're just teaching, then 9th grade is coaching for IIT and all this stuff. I mean, it's just amazing the system is, right? So, I mean, first let's fix the system, understand really, get the kids to, enjoy education, right? So, but what I just told you is no 3rd grade effort. This is called Monte Carlo simulation, by the way. Okay, what I just demonstrated is Monte Carlo. It's a graduate level topic for 3rd graders. Okay, so when I'm talking to you about modeling, this is kind of the start of modeling, right? And if you really ask me, what I'm trying to do is finding the area under the curve, right? So now I'm coming to calculus now. Okay, so now that I've come to calculus, then you start to wonder, wait, this problem has something to do with that problem. Now you start to relate things that you are learning in high school and then connect the textbook approach to a practical approach. So what I demonstrated was a practical approach to modeling to this thing, right? And then you see, oh, I could do the same exact thing with dots. I could throw lots and lots of dots. I could see how many fall under. I could see how many fell in the whole thing. Wait, this is a rectangle. I know the area of a rectangle. I learned it in 3rd grade or 4th grade. I just take the ratio and multiply by the area of the rectangle. I just have the answer. Such a crude modeling, but it's actually not bad, okay? So, this is helpful for children. If there's a multiple choice test, they can avoid those answers that is bigger than the area of the rectangle. Now those kids are going to do very well in life because they really are thinking in an educated way, okay? So all the things that you have seen so far, and I'm going to show you a little more, these are all physical systems. It could be solving, SARS or, all these are physical systems. You're going to come up with mathematical models, and then usually you go for a textbook approach to solving mathematical models. And so then you get what is called as exact solutions. But most of the time, life is not easy for us. The problems don't have textbook approaches. So it's mostly non-linear, the word that the Vice Chancellor used. So you don't have straightforward answers. So you have to have numerical methods to solving this. So many of us spend our life coming up with fast, cheap, and accurate. These are the 3 golden words for people working in my area, computational mathematics. Okay, fast algorithms, cheap algorithms. That means how cheap your resources are, and how accurate can you be? Because I'm not going to get the textbook approach. But the problem with mathematicians is the following. We are pretty good at theory. We are pretty good with computer simulations. What we are not good at is this one, is experimental data. We don't know what happens in a biology lab. And so it's very important for the mathematicians to get this cross-disciplinary training, and biologists to get the cross-disciplinary training this way. So especially if you want to have your research complete, you want to bring these 3 together. So theory drives numerics. Numerics will dictate what type of, ultimately it's all dictated by data. So I'll talk about data a little bit, and with respect to time, I'm going to skip this whole thing, and this is just showing you can write a program and all that stuff. Very simple code. Maybe we'll do this as the first exercise in the afternoon, just to get you excited about Monte Carlo simulation and all that. Okay. So this is the spectrophotometer. The chemistry. So go back to the chemistry teacher. I give workshops to the high school teachers just to get them to understand that a chemistry teacher who is using a spectrophotometer and a math teacher who is teaching logarithms, and the chemistry teacher doesn't talk to the mathematics teacher, and the chemistry teacher is excited saying, wait, I never thought logarithms have applications in life. Well, here it is, right? It is actually the ratio of the absorbance of the intensity with the bacteria and without the bacteria. Negative logarithm of that is exactly helps you to calculate the bacterial density. When the chemistry teacher opens, it's an opening for the chemistry teacher, and of course it's also for the math teacher, because the math teacher is just teaching properties of logarithms, not really saying, wait, you can use it in real life. This is how you do it. Okay, and that's where the interdisciplinary research starts to. So now that we have done high school, let me walk you slowly to calculus and beyond, right? So imagine you are in a biology lab now, and you're collecting data, and the data is like at 0 minutes. This was the population density. At 16 minutes, this is the population. At 32 minutes, so you can see that the time is doubling here. You're calculating. This is a biologist calculating, and you have this, and then I'm saying fit a model. That's it. Very simple question. Fit a model. Well, let's see how we actually go through this process. You could fit a model and you could put it in your calculator or whatever and figure it out. But let's think through this and really come up with a simple idea to fit a model and see how we could teach calculus in an exciting way. Okay? Unfortunately, I'm going to talk about a section in calculus we don't do well. I mean, we just teach just because the book asks you to teach this way. I'm going to get to a point in calculus which you'll see that it's already, oh, this is a cooler way to teach. So for example, if I start the class with the data and say, let's model this. So first thing, when you say model, what is the first thing that strikes your mind? What do you want to do? Yeah, already people are showing this. That means you want to put it in a graph. So you're going to put it in a graph, right? But not just without any understanding. You want to look at the data and say, wait, this is like every time the time is doubling, something is happening here to the bacterial density. But you know from biology that cells divide in half. So this is where a mathematician needs to talk to the biologist. And so now you can put it on a graph and then you get a graph like this. Clearly you cannot put a regression and just draw a line, which is what the first mistake in modeling is. They'll say, oh, now I'll fit a line because I know how to do it. I know how the calculator does it. I know Excel. I can do all these things and all that stuff. And I can tell you about 50 to 60% of the people will fit a line and job is done. That's where the first failure is. Okay? And then this is where you want to look at the data very carefully and say, wait a minute. If I normalize it to 0, 1, 2, 3, this is like the doubling time. Is the population really doubling? Is 22 becoming 44? Is 44 becoming 88? It's not really doubling. So it's going away from the biology. Biology says it should be doubling, right? It's not really doubling. So then you realize, wait, it's probably not a linear model then. And then you ask yourself, why don't I look at the change that's happening? Why am I looking at the change? Because of the change, y2 minus y1 divided by x2 minus x1, now I'm talking middle school quantity called slope, exactly. y2 minus y1 divided by x2 minus x1, if this number is the same, then yeah, you got to have a line, but it's not a line clearly because this change is not constant. So now you realize, wait, the model is becoming more interesting, right? Even though it's simple data. So now you're saying, okay, now let me try to actually plot So it says that bacteria then takes longer than 16 minutes to divide. That's the first opening for the mathematician, saying, oh yeah, now I realize something interesting is happening. And so that's more than one time step to mature and divide. Now you're talking biology language, right? So once you have that, then what I wanted to do is now let's plot the population change versus time. So P at t plus 1 minus P at t, and plot the change. Now the graph starts to look a little more interesting. So you have plotted this thing, and then you're saying, okay, this seems interesting, and then you visualize that one. Once you visualize that, then you get some biology, and cells reproduce dividing into 2 cells. Each cell takes about the same time to mature, and so you have this data. Then you realize that, well, if it is exactly doubling, what will the equation be? P of t minus 1 minus P of t should be equal to what? If it's exactly doubling, should be P of t, right? So it should be P of t plus 1 minus P of t is P of t. So P of t plus 1 is 2 times P of t. But it is not. It is something smaller. It's something smaller, as in it is some fraction of P of t. It's not exactly P of t. But we got to find the fraction now. But that's great. All I have to do is pretend this is y, pretend this is x. You got y is equal to cx. Oh wait, let me just plot this and this now, right? This is how you think through modeling, right? So let me go through this thing, and lo and behold, oh, there's the line. There's your straight line. That's suddenly magic happened, right? Now you are in business, because I can put a line now. Now you use your Excel or whatever and find your thing. Now I'll believe you more as a better researcher than the first time, right? Unfortunately, now that 60% of the population really needs to get trained on modeling and research, because they just do the basic stuff. It's these guys that really see it, realize they get closer to the answer, and then they start to realize, oh, P2, so they find the slope, and the slope is 2/3. Now you hit it with mathematics. What is this? Telescoping series. You can start, say, Pt plus 1 equals 5/3 P of t. Then I can keep going all the way down to P of 0. Now I go back to this thing, and guess what? I found an exponential model. The next time somebody tells you an exponential model, challenge them and ask me, where did this come from? Help them explain. Whether it's a seasoned faculty, I'll tell you, many of them have no idea. Okay, so you really have to understand where it came from. This is presented in calculus, by the way, as recursive or explicit. Take your calculus textbook, any of the books. They'll just say in like 2-3 sentences, oh, this is useful for bacteria counting. That's it. Okay, but this is reality. This is how you actually get towards a model. This is great. So you actually learn some mathematics, and you learn some this thing, and you're getting good at calculus and all that. And then what do? You want to check how good you did. And so to see how good you did, you take this model and try to actually see what the model is predicting, and saying, oh yeah, this of course has to match because it's initial, but look at the numbers here. And you're so happy. You publish this result, right? This is say, oh, I published my result. And guess what? The same biologist that gave you data suddenly comes to you again and says, hey, Padu, I forgot to give you the rest of the data. I forgot to give you, I had it, I found this sheet in my drawer. Here is the rest of the data. You just published a paper with some garbage data then, right? And you got a model and you published it. And then you realized, wait a minute, and you plot this one, and this model is going like this. But then you just figured out that it's an exponential data. Now who's wrong here? The guy who didn't give you the sheet, complete data? Of course, everybody is wrong here, right? So the whole point is, this is how the business is. I want to make sure you all understand. This is how, you realize, like, oh, yeah, if somebody is claiming that they are very good at something, challenge them. Is this true data? Is this every data? Is this all? So when you do that, then now you have a new. But mathematicians are very good at this. They say, oh, now I can write my next paper, right? So, they're like, okay, I have 2 more papers I can write, okay? So, now I'll write with a new exponential model, right? Or new model. But wait, that's great actually, because now you start talking about carrying capacity. Wait, this is going like this. So maybe there is some place, and you start to think, wait, of course, the bacteria is growing. There is no food after a certain point. So all the bacteria are going to start to die. So it cannot just keep growing. So now you put biology and reality into picture, right? So now your model is becoming better and better. So now you have carrying capacity and all that stuff you can bring into picture. you can start to change the model, you know, how much fraction and all that stuff. I'm not going to go deep into it. And you start to change the same exact model that you had a little bit, and you call it logistic regression, right? A logistic model or whatever it is. And then you have a new section in the calculus textbook, right? But you can create a whole calculus textbook completely differently, starting with the problem. So, and of course, you know, I'm just going to go through, this is the standard exponential model that you all know. Now you know that the model that we are studying is almost, you know, completely wrong, right? That's why I want to make sure that we understand. I'll tell you a little more example. So you know that the traditional way to model a population is that it's simplest way to model a population is that the derivative, the rate of change is directly proportional to the size of the population, which means it's some constant times the population. Then you do your famous separation of variables, and then you can get your exponential model. But then you want to expand it to, say, predator and prey. The Canadian lynx and the snowshoe hare, very popular interaction. One is eating the other, and then how is the population? One is going up, one is going down, and all that stuff. Well, what do you know? Well, I know a basic population model. What's that? Well, let's try to model it. Let's suppose this is the forest, and there is plenty of grass to eat, and I throw a lot of snowshoe hare. What do you think is going to happen? And there is no lynx around. There is no this guy around. So what happens? They eat, they reproduce. That's an exponential model, because you learned in calculus, by the way, remember? And so that's this one, right? So dy dt equals to some rate, they grow at certain rate. But now I'm going to be really a bad person. I'm going to open the door and throw some Canadian lynx. What happens now? The lynx are going to eat the hare. So which means the hare should start to come down. So in the same equation, I should have something that talks about the dynamics of the hare. And so it will be, and it has to be negative because it's going to bring the population down. And it has to be an interaction term between the x, which is the lynx, eating the hare, right? Simple model. So once you have this, of course, then you can say, wait, can I change the whole scenario? Suppose this is the forest, plenty of grass to eat, lots of Canadian lynx. What happens now? Canadian lynx are meat eaters. They don't eat grass. So what do you think is going to happen? Die. How fast? Exponentially. So you start with that and you have this one. But now I'm going to make them happy. How? I'm going to throw some hares inside the room. They're going to start eating the hare. So they become plumpy, and so you got the positive term there. So here's your predator-prey model, right? Of course, you got to solve it well post, so you got to give some initial conditions and all this stuff. So when you explain these things, don't just show it as an equation. Where do they come from? So you have to have some understanding. Why is this xy? Why not x squared y? Why not xy squared? Why not x plus y? What's the point of doing that? In fact, this is few years back. I mean, about 3 decades ago, the 5 guys got caught in Antarctica, and they didn't have anything to eat. You probably know the story. 4 people ended up eating the 5th person, and this was cannibalism, people eating people. But then in biology, it had a fantastic term. It was called intratrophic predation. And then a million papers came the next year. That's what mathematicians are super good at, introducing a term and immediately publishing a bunch of papers, right? Intratrophic predation. How did they model it? Fish does this extremely well. Adult fish eating the smaller fish, and also the cannibalism is in many rats eat their own species and all that stuff. So how does the model change then? Well, that's x eating itself. And so then you have an x squared. Oh, new model, new paper, right? So basically, so that's the whole type of thing. But if you actually think about it, that's how that's the way to do research also, okay? So in fact, you could, what we're talking about was just birth rate and death rate. What about people coming in, right? Just look at the border here from Karnataka to Andhra Pradesh to Karnataka. So that whole people migrating back and forth, then dispersal rates. So if you want to actually add these into the model, you could start off with what we did before, which was just this part, and then you can start adding migration of people coming in, the difference of the people, and then some migration term. Call it with some factor, at some rate this change is happening, right? And so if that's the case, and then you have to, now you just figured out that your famous separation of variables technique just broke. You got to have something else. And then you come up with a nice theory called integrating factor and things like that, and then you can actually come up with a solution for that. So once you come up with a solution for that, I'm going to show the solution again. Then you have this growth rate and you have a migration rate. Then you do some analysis. How do you do some analysis? Well, you say, oh, what if the migration rate is 0? There is no migration rate. Well, if that is 0, that's very good. That just drops this term. But I already know that problem, right? I already know that problem is the answer is the original problem. But is this a good problem? Not really. If k is the growth rate, if it's greater than 0, it's exponential growth. You know that it's not, nothing is exponential in each side of the town. If it is 0, then you don't know, population density is not constant, and exponential decay does not happen. Then what about this model? Well, it makes no sense. Move on to something else. Your assumption is wrong. Go for another assumption. So you go for another assumption and then say, oh, okay, let me assume that the migration rate and the growth rate are the same. If you look at a typical math journal paper, you will see these as separate theorems and things like that, right? So, and of course, if you do this, then you are going to say, oh, if k equals to m, this term drops out, and then I can actually drop this term, and then you get this, and then you realize, wait a minute, I have to integrate something. What if this thing is not bounded, right? But let's assume that it's bounded, then I can show you a theorem, new theorem, right? So, of course, if you have to have some necessary conditions for this one, right? So, of course, it's not necessarily possible all the time. So your model is not really, absolutely good. And so then you go for a constant population outside. So you could keep changing the scenario and come up with all solutions. And then you realize, okay, the same setup under these conditions, it's not possible. So whatever model you produce, there's always somebody playing devil's advocate. I want you to understand that. Don't think your model is like the model that's going to solve everything. There's always a devil's advocate waiting to challenge you with a counterexample. Okay? In fact, when I studied topology in BITS Pilani, my favorite book was The Counterexamples in Topology. That's how I studied, that's how I understood topology, is by studying the counterexamples in topology. Okay? I don't know if you know this book, it's a very popular book actually. So, so here's my, one of my first parts of the talk, my big note to you. All models are wrong. Then you're like, why are we having this conference? Because some are more wrong than the others, okay? Because some are more wrong than the others, I can use the other things, right? So, I can always live with some models, not every single model, okay? So, it's not my statement and all that, okay? So, now I've kind of set up the stage for models. Now, I want to take you to frameworks, 3 important frameworks that I wanted to tell you. I personally work, I work with these things. This is the United Nations and UNESCO who created 17 goals. These are the this was the Sustainable Development Goals. It used to be the Millennium Goals, 2015 goals. Everything from no poverty, zero hunger, quality education, gender equality, life below water, peace and justice, and things like that. These are goals set by policy people. But the question is, how do you bring that into research, right? So this is something I'm going to share some examples with, which I've done with my colleagues here. I worked at the National Science Foundation who have their own goals. Their goals are much like harnessing data is one of the places where they want to put a lot of money. Understanding rules of life, they want to put a lot of money in these types of projects and all this stuff. So this is a great place for mathematicians to get involved, big time. So this is the NSF's big data, big research areas. And then I also am involved with the National Academy of Engineering grand challenges. The grand challenges are how do you make solar economical? How do you manage the nitrogen cycle? How do you engineer better medicine? So all these are 14 challenges at very high level. Anybody can, in half an hour we can figure out our own challenges. It's easy to write down 10 challenges, water, traffic. I can ask you to give me challenges, I'm sure you'll give me 50, right? So, but the thing is not to come up with this many challenges. The thing is, how do you take these challenges and make it interesting in a curriculum? Like, for example, I work in that space where Dr. Punch works in. It's called innovation. How do you take these into research in mathematics, into research in product development and things like that? That's where the innovation comes. And that's what ASU is, when he said ASU is number 1 and MIT is number 3 and Stanford is number 2, it's in the space for innovation. You won't have innovation if you don't have good research. So that's where the research and innovation comes in and all that. So I'm going to now shift gears and go through some of these frameworks and how these frameworks lead you to good research problems in the next 15 minutes, and then I'll stop. So, so the first one that I want to focus on is good health and well-being. And I'm not going to spend a whole lot of time because this is you already have 2 distinguished people who already talked about it. What do I mean by that? The same models that you've already talked about. The SIR is what Carlos and and Anuj presented for going from susceptible to infected to recovered, or SIS, time, most sexual diseases, you can become susceptible again. And then you have exposed phase sometimes with vector-borne things, mosquito disease, vector-borne diseases. You could have different types of, these are compartments that you can come up with. With these compartments, you can come up with system of equations and all that. So for example, if it's a susceptible, people in the town are susceptible to a disease, they get infected and then they get recovered, go to the hospital, get recovered and all that. Of course, they have their own favorite equations. You all know that this is the recovery rate, this is the rate at which, this is the recovery rate, and this is the way, this is the transmission rate. Okay, so I'm not going to give you anything new that you don't know. So in the afternoon, we'll quickly model these things using finite differences. This is, of course, Euler's method, and simply, and I don't want you to, if you don't have anything, if you don't have Octave, or you don't have MATLAB, or you don't have R, what do you use? Well, something that we all know, Excel. Why do you have to have like fancy stuff? Just use Excel. And when you use Excel, you will quickly, you can put these formulas in and you can quickly generate all your graphs and all that stuff. You don't need anything more than Excel. You can do it on your sheets, Google Sheets on your thing and all that stuff. You can teach little kids to do it. In fact, I'll tell you how I bring it to schools and all that. So in the afternoon, we'll also talk about an actual data that Carlos pointed out. This is the London boarding school. One child went to Hong Kong and then returned, and that child came with a flu and then started infecting every other child in that school. So there were 763 children there, and so how did that one child, so this is like, when the child came, how the disease actually, everyone else started getting infected, and people were put in quarantine, and basically the convalescent group of people and all that stuff. So you have this type of a data, but then how do you take this and then make policy decisions, right? So that's where we'll do this in the afternoon. And I'm actually going to skip these things because we're going to talk about this in the afternoon later on. This is what I ask students to do, is to have a front-end tool which you can put on a cell phone and quickly do these things and all that stuff. So I'm going to skip this because of time, but I want to just build on the modeling side. So okay, now I know something like SIS model or SI. So what about I add this term here? So it means now I'm adding something like births, then your model changes. So once you have that, maybe you can actually study those in terms of the dynamics and all that of this model. So look at how simple the ODE system still stays as the ordinary differential equation system. By simply changing one term, you have a completely new model. But then you could bring in a logistic version of it. That's a different model. Once you have that, then you can actually start talking about what about diffusion. Somebody asked about partial differential equations. I think you specifically asked about fractional also. So, and I think Carlos's answer in terms of the age structure is a great way to bring the connection and all that. Okay, so that's a very nice way to actually segue into some PDEs, for example. And then you can actually find out how fast it grows and things like that. And then of course you could do it for both SI. You could even do it for the whole SIR, everything, and you could bring diffusion, and you could make the problem as complicated as you want. Okay. Point is, does it simulate reality? That's the whole point, right? So now I want to shift gears. As I said, I'm going to just check on problems. So the next one I worked on was clean water and sanitation. So what I wanted to do was not the mathematics to drive the challenge, but the challenge to drive the mathematics. So I take a challenge like, oh, clean water. What can we do with clean water? Well, clean water and life below water. So if you actually, and good health, well-being, I'll tell you what is going on here. And you could see provide access to clean water is also in the National Academy of India, for example. 163 million people lack access to clean water. Okay. So in terms of contamination, you can see how many, about close to 2 million by chemical contamination by water. Just debris, like garbage that we throw in the sea, in the water, right? So this is World Health data in terms of all the things, and this is not, you can easily Google and find out all this data. Okay. So the question is, more than 100 million people live in areas of poor. There's your problem staring at you. How do I turn this into mathematics? That's the problem. That's what our system is not trained to train you. When I say system, I'm talking everybody here. Okay. So everybody here, how do you take something like this and bring it into the mathematics classroom, right? So, and that's where the research is, and that's where things like MTBI is great, because when kids are asking questions like this, what are you going to do? Where do you even start? Well, you can say, okay, villages, Here is one side of the village and then another side of the village, so that's 163 million people lack access to safe water in India, okay? And 210 million people lack access to improved sanitation. 68.8% of people don't have place to go to bathrooms. I'm working with Jamia Millia on a social project, social work project, to actually, with machine learning, to find the ideal locations for bathrooms, mobile bathrooms, okay? They came up with the concept of mobile bathrooms, but where do you place them, right, in an optimal way? So imagine a water body is shared by multiple villages, right? And they're all sharing this water. What can you make this interesting? By the way, the project was with 2 high school students, and I'm not saying that high school students can't. I mean, I'm telling you, there's lots and lots of students can actually do high school student research also. So imagine just like a water body being shared by this thing, and you have the rates at which people are drinking from and things like that. And now all I have to do is take the SIR model and start to introduce interactions with water, right? And then instead of a SIR, you got an SIWR model. I was talking to Caesar yesterday. He said, oh, this is exciting to me, but can I bring economics? Of course you can bring economics. Just put some yield inside here and make it stochastic even better, right? So now you have 2 villages sharing. So now you have your SIR-WR model between 2 of them, right? Once you have that, then you have an equation for water, because pathogens inside, how are they actually interacting and things like that, right? Now you got the model for at least 2 villages. And then from there, Excel is my friend. I mean, this is, when I train high school students, first thing I say is, oh, let's start with Excel, okay? And then they do Excel. They have their graphs and things like that. They understand these models and things like that. And then I ask them to go find their own problem. Then they say, oh, rainfall. How does rainfall affect this thing, right? So one student was interested in the rainfall aspects of it. So she went and said, oh, I'm going to incorporate rainfall into this model. Okay, go for it. So if you want to incorporate rainfall into it, and then you can actually start to add rainfall terms into it and things like that, right? This may not be the best model, but this was our idea, okay? And so then what about the other student wanted to actually come up with a device for India. I said, okay, great, come up with something. Excel is not going to cut it, but just the concept is okay. So he said, oh, what if I ask all the villagers to just punch in something into a Google form just with a cell phone and all that stuff. The SMS just simply sends it into my Google Sheets. Google Sheets, it will come into my SIWR models. It will update the model and immediately tell me, this village should not drink this part of the water. That village, you're okay to drink it here. Just an early warning system. Now imagine the impact that you're making. Just with, now you're talking product development. Now people like Punch will get excited because product development will lead to technology. Technology will get people like Google and these guys to say, oh, how can I fund you, right? So that's the path towards your. So of course you have to go through these types of things and all that. This you already know good. About the SIR model. But then when a mosquito is involved, then it's a vector-borne disease. So when it's a vector-borne disease, then you have much more than then it becomes not just studying the humans, but you have to incorporate cycle for the mosquitoes too. The mosquitoes also have their own. And a classic example, Zika. So why is Zika very, very interesting? In fact, I have to accept, I'm not from the infectious disease, but I learned the little bit I know from, being at the MTBI, and then I got excited, and then my daughter went to MTBI. She came back excited after seeing Carlos and Anuj saying, oh, this is very interesting topic. She had absolutely no idea about mathematical biology as one of the things she wanted to do. But now she's going to be starting a degree in mathematical biology and a degree in neuroscience, but she always wanted to become a doctor, and somebody said, to become a good doctor, make sure you have a good math or a background that's completely different from what you become as a doctor, because they're going to go through the 7-year residency and things like that and all that stuff. Why is Zika interesting? Because Zika puts 2 different theories together. Theory of direct transmission and theory of vector-borne diseases. So when you put them together, your R0 things and all will start to take different shapes and all that stuff. So it becomes interesting. So we were fortunate to actually work on, the infected mosquito, biting a healthy human, or uninfected biting like a healthy human and things like that. I mean, a healthy mosquito biting an infected individual. And so you saw this picture that Anuj showed, and this was in the Siam news and all that stuff. So when the student came back, this is that's, you can see my name there. That's my daughter, with who was fortunate to work with Castillo Chavez. And so this is a paper that we wrote, which is in the same journal that many of you are going to hopefully submit. And what she was interested in is, what if I bring nets and sprays for Zika? How do I bring that into the model as a preventative measure? Okay, and so that's basically, by the way, I have to tell you, this was when she was a high school student also. So, and I'm going to skip this because, what was interesting about this model is we brought that infectious into an asymptomatic and an asymptomatic, and we had things like nets and sprays and things like that. And so, again, we consider two different classes. I'm going to skip these things. Again, the same model. Let's see. So those are like additional things. So if you take models that, so this is research. So we took the paper from the Columbia model, that the Barranquilla that he showed, and said, oh, let's incorporate nets and sprays into it, and then see what happens. And we had these different, of course, we derived the R naught and things like that, and then we got this massive. So of course, it becomes a new theorem now, and then we did some simulations for different types of nets, different types of sprays. What does the R naught look like, and things like that. What happens when the sexual activity increases, what happens to the R naught, and things like that. So these are things in the paper, so just to give you an idea. So let me take maybe 5 more minutes and wrap up. Peace, justice. So you're wondering, how can I bring peace into mathematical modeling? Well, interestingly, I work with my colleague who's sitting here, who will talk about this tomorrow. This is Professor Carmen Caicedo from Puerto Rico. One of the pictures that I showed you at the beginning was about gangs. So when she brought me a student and we mentored together, the student, we asked, boldly, what do you want to do? He said, my cousin got recruited into gangs. Can you help us, can you help me do mathematical modeling of gang violence? So we were like, okay, where do we start? And so what was interesting is he had lots of data, lots and lots of data for gangs in Puerto Rico. And so it was about recruitment. Then we started talking, and then this person met the Zika student, and they started talking. And believe it or not, before we knew anything, we had to decide. These kids had already come up with their model. They said there's the youth gang, there's the adult gang. The adult is like the mosquito going and infecting a youth. And they came up with this fascinating model. Hopefully, we're going to write this up for this journal publication, hopefully. So very nice. They got superb results. They derived their R naughts. They had their things and all this stuff. They learned something. That was the whole point. Okay, and this is an undergraduate and a high school student. Okay, so and they came up with all these different types of things and all that. Quality education and reduced inequalities. One of my favorites. I'm very big on. Two problems I'm going to tell you. This is about education. So this is Houston, Texas. The two regions that you see are populations of people. One is the white population and one is the Hispanic population. Hispanic population, so many of them have in the schools special teachers. They're called ELL, English as second language learners and all this stuff. What the politicians do, of course, they don't care about education sometimes. So in Texas, what they did, they went and rezoned everything. That means just before elections, they rezoned who can vote in what district. So what happened doing that, well, the elections was improving. What was a big challenge was, what do you think was the challenge? The schools in the US are all free, by the way. Public education is free. So, but if you are a Hispanic child and you're going to this one particular school and you have a special education teacher that helps you to learn the subject better, if by redistricting, the schools go to a different county. That means you just lost your teacher. They didn't think about the children getting affected. So this is a student personally wanted to do this project, but this is not interaction. This is social dynamics. Somebody asked earlier, this is about people interacting with each other. So the question is, this is not an SIR model, but this is people moving back and forth. But what is interesting is this is the student who came from Texas. She wanted to solve this problem because her friends got really affected because of this. We said, okay, United States, Mexico, and Honduras. Let's expand the problem to two different types of population. Adults, children, stolen in or running away from gangs. And how do we actually model that? And she modeled it, came up with her own social app, Dynamics app. This is in the White House meeting Mark Warner, who was the former governor of Virginia. But it was a mathematical study, basically. Okay, and Two more applications maybe. And another favorite of mine, this is very big problem in the US. I mean, I know only few people like Carlos who has managed to solve this problem. Women, look at the crowd here. How many women are sitting in the audience? Some of you are not even in academics. Look at, if I can count by fingers how many women to men are sitting in this audience. Maybe it's because of, I mean, I don't know about the situation here, but I go to Myanmar and I saw the same situation in many, many countries. In the US, it's worse. And I think, you know, for people like Carlos who are like really changing the game in terms of the number of women getting PhDs, that's something really, really important. So for me, it is much more important because here's some data like STEM PhD holders, they come into school, they look at a faculty member teaching, and then they leave. They say, oh, I don't want this. I don't want physics. I don't want chemistry. This guy is not teaching to me. And that's the problem. You know how many women leave the industry, leave academics this way? Female STEM PhD holders leave STEM. I don't have the data for, I have for African Americans, the data is like 1 in 5. Okay, so it's and it's amazing how the other countries are doing something very different. Okay, in terms of the number of women in Iran, it's amazing how many women are in. So I had to create something, right? So Carlos, we always try to figure out, okay, how do we solve this problem? Well, I attacked it much earlier. Of course, Carlos is doing at the research level, which is great. But I said, oh, I'm going to just bring high school girls into campus, middle school girls into campus, and I'm going to get them to enjoy STEM. But I'm not going to just help them play games. I want to really seriously give them some high-level stuff, drones, 3D printing, something pretty high level to get them excited already, talk about math and drones and things like that. Of course, the moment I did this, they put it on NBC, which is the National Broadcasting Corporation, because this lady that is standing here, she reads out weather every single day. You know that lady that comes and says, today's weather will be, today's, in Tamil they say, Angange Malai Peyyum, or whatever it is. Nobody says, where is that Angange? Engeyo, wherever. Right, so so that's the problem, right? So like with this probability or something like that, they have no idea. They are reading out some report, right? Sometimes and all that stuff. But it's interesting that you can excite children by asking those types of things. And then, of course, now it's self-funded. I have 100 girls that come. I mean, companies are fighting to fund me on this program. They said, please, I will put money on this program and all that stuff. So this is 100 women every summer I have. And now I have a high school academy, which is basically research. Now we turn this into undergraduate research and so on. And here is, in a physics session that they are engaged in solar pumps, and I'm asking them questions like, what if you move there's the solar panel and there's the sun. Sun is the table lamp. What if I move the table lamp double the space? What if I do 4 times the space? What do you think will happen to the fountain's height? I'm teaching them ratios and proportion, right? Middle school. And then what happens if I close the area? Well, like 3/4, 1/4 and things like that. What happens with the height of the fountain? And so ask these inquiry-based questions and all that. It makes it more interesting. So in interest of time, I'm going to just move to finish this thing. So these are some of my projects from an institution in Africa. I have a PhD student from Africa who's here also. So this is, just to give you an idea, this is about population. This student approached me to ask, I want to build more schools. So when the students are asking you challenges, they are saying some things like that, but you have to turn that into a good math problem. So the good math problem was Tanzania's system did not have a good registration system, tracking how many babies are born, how many people die. So basically we took the whole Tanzania, divided into districts. In each district we had hospitals. In our hospitals we had nurses, would SMS. Today 2 babies were born, 3 people died, one of Ebola, one of this was the age and all this stuff. That SMS will go to a master database. The master database will be running a mathematical nonlinear biology problem, which this guy did. So that's his master's thesis and all that stuff. So now we have an idea of, so once you know that it reaches a certain target, you know that you have to build more schools, which was his initial challenge and all that stuff, right? This is corruption. So I like to take these problems because this is impacting the country. So this guy wanted to actually say, no, there's too much corruption in the country in the oil. So they basically go and put kerosene in petrol, the gas station owners, over in the night. So what did this guy do? Well, he came up with a small device that he came up with. So this led to, in the mathematics side, optimal control. And he also was an electronics guy. So, we could put math and electronics together. And this is funny research because it's not happening in the US. In the middle of the night, he will go and put these in gas stations. secretly. The gas station owners don't know. The gas station owners are putting kerosene like at 3 a.m. or 4 a.m. What happens is this device will capture the ratio of kerosene and petrol, and then it will say, I am pure or I am adulterated. When you drive your car, you know that, oh, I don't want to put gas here. Let me go to the next gas station and all this stuff. But even better, once it says I am adulterated, a message goes to the Tanzania, the transportation, goes to the police, they'll come and catch the guy. Now think about your master's thesis doing such a big change in a country, okay? So you need to have the government behind you for these types of things and all that. But it's research, why not, right? So here is, predator-prey can be turned into mutualistic models. So we try to use mutualistic model like nitrogen helps legumes grow, and legumes help the, bacteria, sorry. Rhizobia is a bacteria that fixes nitrogen for the plants. At the same time, you have the, the bacteria also eats the legumes. So it's a two-way, it's not a predator-prey, it's a mutualistic. But how can I take it to the next level? Well, with Dr. Caicedo, this summer was very interesting for me because a student from Puerto Rico came again. And this student's thing, his dad is a farmer, and he was devastated when the hurricane came. The whole Puerto Rico, I hope you know what, just like Kerala, what is happening right now. The entire thing was demolished. Like crops, everything, this is banana plantations, completely demolished. So how do you come up with some interesting ideas? So he was interested in coffee plantation, which is completely destroyed. So he realized that coffee and bees have a nice relationship. So it's about coffee and bees, that's the C and the B, and this is how the mathematics is coming in. And this is how, different types of interaction, and he just finished his research on this one, and this is the program with Nelson Mandela. So in interest of time, because I'm standing, this is my favorite one, which is poaching. Every 15 minutes, an elephant is killed in Tanzania. So this is how we took a problem from something like that and then went all the way to applying, and the solution, this is Eric Masavi from the same institution. The solution was a drone, and the drone actually monitors, but is there mathematics? Sure, there's lots of mathematics. For example, I can talk about the mechanics of the drone. Where does it go from one place to the other? I can talk about control of the drone. So now you have optimal control. And then, of course, I can talk about probability. So this other student wanted to talk about, is the drone looking at an animal? Is it looking at a ranger or a poacher? So, it depends on the guns that they're carrying. Now you're talking about middle school conditional probability, but at an advanced level, using machine learning and things like that. So, this is actually what I wanted. I'll present it later on, but this is now, we'll talk about this later. This is an idea of how deep learning, this is the kind of the current trend, can come into infectious diseases. So this is kind of something I'll be submitting with my co-author and all that. It's like, you'll be learning in the afternoon about this S infinity and R infinity. This SIR has like, what happens when the dust settles? What happens at the beginning? All I knew was one boy came, he was infected, and he started infecting everyone else. And you have data. You know nothing else. How do you build the whole story from that thing? So you can actually use what is called as physics-informed deep learning for infectious diseases. Probably the first paper in this area that we are writing. This is with my former student who's at the faculty at Brown University. It's about how do you actually turn those physics, how do you bring the physics inside and find everything that you want. Alpha, beta, S naught, I naught, S infinity, R infinity, everything in one shot, okay? And so you use what is called as hidden layers, neural networks, and multiple hidden layers. I'm just showing you two of them. How do you go from all the way from T to SIR? And then this part is physics uninformed, and now you inform it with the physics using automatic differentiation. That's where the uniqueness of this thing is. We use TensorFlow and all those standard toolboxes. We are applying it to the same model that drove these epidemiology and all these areas, infectious diseases, long time back. Now with deep learning on those things and all that. Believe it or not, just with the infected data, we were able to get the exact thing completely for everything, the S naught, the I naught, the S infinity, R infinity. There are other advanced methods also, but essentially it's kind of like a least squares, but you just with one data known and just the infected known, and we'll talk about this in the afternoon and all this stuff. So I want to finish with a very simple note. So as a mathematician, you really don't know where to fit in. Like, are we fitting into science, or are we Engineers, we don't really know. We are in the space in between. That's why STEM, science, technology, engineering, mathematics is a separate than science, right? Than engineering. If you actually think about the way they think, scientists are always after a question, and engineers are always after a problem. So the way scientists approach problems is like an inquiry-based approach, and the way engineers approach problems is like a design-based approach. Mathematicians are in the middle. We can do it, both ways, and that's the power that we have in terms of bringing these areas together. And I think it's very, very important. And people like Carlos have really done phenomenal work, not just in mathematics space, but in the social space. That's where the real thing is. So don't just do a project just because you want to publish a paper. Do a project so you can change something in the society. Then it becomes more meaningful. Okay, so in terms of so you actually will research the question in science, but here you research the problem, and you test in the hypothesis. Here, for engineers, it's easy to build a small bridge and then break it, and then build a bigger bridge and break it. You can't do this with a microscope in science, right? So you have to have that inquiry-based and the design-based approach to do problem solving. And then, of course, in terms of you have so many things you can take research. You can modify the existing assumptions, take the SIR model, add water into it, add economics into it. So you can keep modifying assumptions, build realistic geometry. That's another way to do research. Optimize the technique. Somebody would have written a code that is 3,000 lines. Just make it like another simple technique and make it like 3 lines or 30 lines, right? So enhance the software or match the experimental data. This is what we'll be doing in the afternoon a little bit, and doing parameter estimation. Thank you for your time. So, okay. So will the evening, I mean afternoon, yeah. Take the disk.
We thank Professor Seshier for his talk. Now we'll break for lunch. Sir, can you moment? Yeah, tokens of love. Sir, let him come. So. I have a small announcement. All the participants will be having lunch in the North Indian canteen. We have Dr. Bhatwaj and Dr. Shyam coordinating for the gents, and for the ladies we have Josna and I forget your name. So Soundarya. Right. Okay, thank you. We'll again meet at 2 o'clock for the hands-on session. Here, reassemble here at 2 o'clock.